All right, guys. I'm tasked with allowing persons to enter the room simultaneously. So thankfully, very thankful that we are doing this primarily from your end. I'm just here for guidance. All right, let's see what goes on. Welcome everyone. We're about to start. Admit. Can I take this out? Thank you. All right. All right. So we'll be doing chemistry. And we have 39 persons here, right? And this is 2021 paper, right? And let's see how best we can go through this paper. So a volunteer who wants to go first. Before we begin, let's just begin with prayer. All right. Let's begin with prayer. All right. Let's pray. Heavenly Father, as we come here before you, I want to thank you, Lord, for giving us the knowledge, giving us the courage, guiding us to do this lovely subject. And even now, as we are about to embark on completing some past papers and getting guidance, Father, I ask that you guide us and give us your wisdom. In your name I pray. Amen. All right, everyone. All right, everyone. Do we have a volunteer for the first question? Feel free to raise your hand. You can unmute your mic. I heard someone who was trying to unmute your mic. Identify yourself, of course. I'd really love to know what school you have attended. But unmute your mic, identify yourself, and I'll acknowledge you. There are no volunteers.
Could you scroll down a little bit?
Oh. So the question here, right? Allow me to read. It's about electrolysis. All right. Student conducted an experiment to determine the products formed from the electrolysis of aqueous copper 2 sulfate using inert electrode. Figure 1 shows a simplified diagram of the apparatus used. See figure 1 below. All right. And now they are giving us a whole scenario, the procedure used, where they said a current was passed through the electrode and the starting time was recorded at 10-minute intervals for an hour. The volume of oxygen gas evolved and the mass of copper deposited is measured. At the end of the reaction, the total mass of copper deposited was 4.85 grams. The volume of oxygen gas evolved is shown in the table below. See table 1 below. All right. Lovely first question. Define the term electrolysis. Volunteer? No volunteer?
I'll volunteer.
All right. Identify yourself and your school.
Sir William Suho, Maths Unlimited.
First name should be fine. William, Maths Unlimited. All right, go ahead.
All right, so electrolysis is the chemical change occurring when electric current passes through an electrolyte.
You're asking me?
No, I'm saying it.
Okay, you said right at the end, so I was wondering if you wanted validation. Validation. Repeat the definition.
All right, electrolysis is the chemical change occurring when electric current passes through an electrolyte.
Okay, right definition. It's a very inclusive definition. It includes a process, procedure. Anybody have a definition? Of course, we're not all writing the same thing. Just unmute your mic and go ahead. Can't really see it.
Sir,
Uh-huh.
electrolysis is the process by which an electric current is passed through an electrolyte to split up compounds and elements and stuff, I think.
So what I like to ask my students is that what you write on the paper?
Yes, sir.
Not you, William. The person who came after you, I didn't get the name. You said compounds and stuff. That's what I heard. What you write on the paper?
Sir, I wouldn't put stuff.
What would you put?
Sir.
You see, I like the definition that William gave me, right? William gave me a definition. Repeat your definition. I did. All right. What's your name exactly? What's your name?
My name is Jade Brown.
Jade. All right. Repeat the definition for me again, Jade. Let's dissect the definition.
So I was saying that electrolysis is the process by which an electric current is passed through an electrolyte and it breaks up the compounds and stuff present or something.
All right. So the stuff you're referring to, are you referring to the molecules in the electrolyte?
I suppose so.
All right. One thing I've realized is normally in teaching they don't teach you how things happen, they just tell you the definitions and stuff. So I trust we all know how electrolysis occurs. So we're here to help Jade. Can somebody unmute and tell me how does electrolysis occur? If you know it occurs, you can just write that on the paper. Unmute your mic and talk, man. Unmute your mic and talk. How does, oh, this is Jade, right?
Yes, sir.
All right. How does electrolysis occur?
Sir, the ions with a negative charge will be attracted to the anode, and the ions with a positive charge will be attracted to the cathode. So by that happening, it kind of splits them up, and then some of them get discharged and stuff or something.
All right. So what is the context of this? Is there a container? Is there a, what are the terms that you're using in electrolysis? Anybody want to help?
Aqueous.
Pardon?
Molten or aqueous.
Molten or aqueous. Anybody else want to help Jade here? How does electrolysis occur? Jade, I appreciate your answer, but it's a little bit out in the wind. Unmute the mic and talk, people. I saw hands up, but I can't really see. Come on, man. There's no wrong answer, you know, it's just what you know.
Sure.
Jade? Wait, Jade. Who is talking now? Name, please. The person who said, sir.
Can I go?
Yeah, go ahead. Guys, look, all right, let me make this clear, right? I'm coming to you, I'm genuinely asking what these things mean to you, right? So there's no wrong answer, because whatever information you are presenting to me, that's what you have been presented from either your teacher or another source of information. Understand that. There is no bashing in saying, oh, you don't know this, or oh, you're not supposed to know that. Look here, I'm telling you something. I'm here to help you, right? And whatever information you have presented, right? It's above the average person who would know things like that. The average person is not going to know electrolysis. Average person is not going to know other terms we're going to deal with today, right? So let me make it clear, everyone. You're coming today, you're going to ask questions. Okay, what do you know? I'm asking because I'm coming from a position where I want to help you. Person who just entered, I think it was Walker. I think your mic is unmuted. Person just entered, was Walker. Your mic is unmuted. All right, somebody is unmuted. So let me see if I mute everybody. All right, is there still a feedback? Let me see if that, okay, all right. All right, so that being said, right? That being said, I'd like someone to tell me, right? How does electrolysis occur? Come on, guys. It's about what you know, right?
Okay, so I'm Alex McDonald.
Mm-hmm.
And based on what I know, electrolysis is when there is two electrodes and an electrolyte, and electricity passes through that. So the electrolyte will be molten, for example, sodium chloride, and the electrodes would be the two, on the image you had before, the two battery-looking figures. Yes, and
What anybody want to give us what the name of those two things are?
Cathode and anode.
yeah, the cathode and anode.
What's the general name for it? You don't have to say cathode and anode. There's an E word.
Electrode.
Yes, electrode. All right.
The anion would be attracted to the anode and the cation would attract to the cathode. So electrolysis would occur and the calcium, not calcium, what I say, sodium chloride, the chlorine, yes, since attracted to the anode, it would be deionized, I think, and will be returned back to its original form as chlorine gas and then released off, while the sodium would lose.
All right. Wait, Abikela. I'm gonna forget your name, right? Wait. So you're giving us a very specific example, right? Your framework, you started out good, right? So some key points noticed in her response, right? She spoke about the presence of electrode, right? And she spoke about the presence of an electrolyte, right? Then afterwards, she spoke about electricity being passed through this electrolyte, right? These are the steps in the procedure she's telling me about, you know. And she also spoke about the electrolyte being, some parts of electrolyte, the anode being attracted to the anion being attracted to the anode, and the cation being attracted to the cathode. I stopped her there because she was going in all specifics about breaking up molten sodium chloride. She also spoke about the electrolyte being either molten or aqueous. So if we understand those key concepts, right, we can form a definition. For example, the definition from a popular book used in CXC is electrolysis is a chemical change, right, which occurs when an electric charge is passed through an electrolyte, right? So they're speaking about one, the chemical change that occurs, that is the splitting of the anion, the cation, right? That's a chemical change. Recall what a chemical or physical change is, right? They speak about the presence of an electric charge, or as we normally call it, electricity. And they speak about the presence of the electrolyte. I mean, you can always add on to it. You can say passing through a molten or aqueous electrolyte. You can add on terminologies to it, but it's as long as you can present the examiner a definition of what electrolysis is, you should be fine. Kayla, this is 2021. Is it CSEC chemistry? Yes, it is. So Jade, your hand is still up. You want to augment your answer now? I hope you understand. When is Cape chemistry? Cape chemistry will be held, well, we don't have it formally planned for Cape chemistry to be held. They're on. I hope you're in the group. If you're in the group, you can contact, I'm Alex, I'm the 402 number. So the next admin in the group, you can contact her and we can see if something can be worked out, but formally we don't have anything planned for Cape chemistry this year. Jade, your hand is still up.
Yes, sir. Okay, so could I say that electrolysis is like the chemical decomposition of an electrolyte by the passage of an electric current?
Loving that answer.
Sir.
Loving that answer. Loving that answer. I'm fucking it. Clapped. Loving that answer. So you're incorporating what you know about chemistry, and you're presenting the examiner with an answer that demonstrates you know what electrolysis is. From you do that, you don't have to SWOT anything. It's about understanding the core concept. Teachers don't normally do that because it's a lot to cover in 2 years, but I find it's a lot easier, and it allows people to make a decision if they want to continue chemistry from earlier and don't get stuck in this thing. All right, next question. So just
one thing. Wherever you say a definition, you can type in the chat.
Jade, if you don't mind, type a definition. I hope you still remember the definition. I want to move on to another question without much time. I want to complete as much thing as possible. So Jade, you can type a definition in the chat. And William, I believe, William, you can type a definition in the chat as well. Those 2 definitions are really good, right? But what I want for you to understand, everyone, right? If you know what electrolysis is, you're quite fine. And you can always rewatch recording. We spoke about the key concepts that you should make note of when you're thinking about electrolysis. I spoke about the whole process of electrolysis. So there's always that. Okay, let's see. Next question. I hope William heard. William and Jade, you can write your answers in the chat for those who would like that opportunity there. So just one material that could be used for an inert electrode in the electrolysis of copper 2 sulfate. Somebody else.
Graphite.
Graphite. Who's that?
Zariel.
Zariel. All right. Graphite is an answer. Yes. All right, that's the one you're exposed to at this level. All right. Let's move on to the next one. Using the data in table 1, this table here, plot a graph of volume of oxygen measured versus time. Using the axis in figure 2 on page 7. Draw a split line. All right, so I'm going to assume that we can all draw a graph. I'm not going to go through that per se, but I went ahead and I plotted the graph so we can answer the question here. So I'm going to assume you can draw the graph, all right? I hope that's not a huge assumption. Please don't be a huge assumption, guys. For those who can draw a graph, you can raise your hand in the chat. I don't see anybody hand. Great. 2 persons can draw a graph. All right. 3 persons can draw a graph. 10 persons. All right. Looks like the majority of us can draw a graph. This is good. Good news. All right. So I went ahead and I plotted this graph on Excel, right? This is the graph. So I hope you're seeing my screen. It should be. I think it's lagging. So the question is, let me repeat the question. Use the graph to determine the time it took for 5.5 cm of oxygen to be liberated. So determine the time. How would you tell me the time? How would you read off the graph and tell me that? The time it took for 5.5 cm of oxygen to be evolved. You can just talk. You don't have to raise your hand. Just unmute your mic, identify yourself, talk.
Sir.
Uh-huh.
You can draw sir, you can draw a line from where the thing is, and then where it cuts the axis thing, you draw another thing down at the bottom, and then you would count how many minutes this where the line would go.
Where we're drawing the line?
Sir, you're gonna draw it at 5.5, and then where it cuts the line, where it intersects the thing, you just draw down.
Also, we draw across here, and where it cuts here, you draw down.
Yes, sir.
All right, no problem. Hope everyone got that. So 5.5, identify 5.5 on the y-axis, of course. I should have had my titles. So this is the volume, and this is the time axis. Yeah. So you identify 5.5 cm cubed on this axis. You go across where it intersects this straight line here. You go down on and you find the point on the x-axis here. All right, let's move on to another question. I see some hands up. If there are questions, you can just feel free to unmute. I'm not really able to see and do all this multitasking at the same time. If you have a question, just unmute, go ahead. Guys? No question? Okay, no problem. Identify all the ions present in the electrolyte used in the experiment. All right, let's go back up. Anybody? Identify all the ions, all the
Sir.
ions. And this is Jade.
Yes, sir.
Wait, Jade, wait. Let me see if I can find somebody else, guys. It's just Jade doing exam. Jade, then your hand is up. Remember, you can't just unmute and talk, you know, guys. Jaden, go ahead. And Jaden doesn't want to talk to me again. All right. Next person, I think Jaden, is that you? No.
I could answer the question, sir.
You want to see the question?
Yes, sir, I'll answer the question.
You said you will answer the question?
Yes, sir, Jabari.
Jabari?
Jabari, yes, sir.
All right, no problem. Go ahead.
So you would have copper 2 plus A hydrogen, OH minus, and SO4.
You said copper 2 plus. You have what else?
Hydrogen.
Hydrogen.
OH minus and SO4.
OH minus and SO4. All right. So the question I have for you, Jabari, is hydrogen an ion?
That will be the H plus, sir.
H plus. All right. State symbols, yes, preferably. But of course, we know that ions, they're not solid, they're not liquid, right? They're not solid, they're not liquid, they're not gases. So ions are automatically like aqueous. So you can include it, for good measure. It should be necessary. All right, so Jabari said that there will be copper 2 plus. All right, he said that there will be H plus ions available in the solution. Let's see if I can find H plus ions in the solution. Jabari, where would these H plus ions come from?
Because it's an aqueous solution, meaning it's diluted or dissolved in water, so it have H plus.
Okay. And what else you said was in it?
The OH minus.
And
the copper and the SO4 sulfate.
All right, no problem. Good answer. Good answer. Next question. P and Q are electrodes shown in the apparatus used for electrolysis in figure 1. Do you have a question? No question. All right. P and Q are, all right. These persons who have raised their hand, they can answer this question. State electrode in which electrode is the anode, which electrode is the cathode? Up here, which electrode is anode, which electrode is the cathode? You can unmute and speak, guys. Who is this?
Jana, Manchester Echo.
Jana, all right, go ahead.
The P is the anode and Q is the cathode.
The P is the anode and Q is cathode. All right. The P is the anode, you said?
Yes, sir.
Okay, and Q is cathode. All right. I saw a name. Somebody raised their hand just a while ago. He just hand is dropped down. All right, so everybody understands why the P is the anode and Q is the cathode. All right. So moving on, next question. State one ionic electrolyte that will drift towards the anode.
OH minus.
OH minus will drift towards the anode. All right. So state another one, because we're not all going to answer OH minus.
Sulfates.
Sulfate. So this S. What's the formula? Formula unit.
SO4 2. The SO4 and then a 2 minus at the top.
Okay, no problem. That's good. All right. It's going to be a little bit physical. Let's see if I can allow. Can I allow the writing? Or I can probably write. Let me write. So tell me, guys, how would I answer this question? Write an ionic equation for the reaction taking place at the cathode. Reaction taking place at the cathode. Wait, identify yourself. I want a new person.
It's Jade Brown.
Who is this?
It's Jade Brown again.
Jade. Oh my lord. Yeah, you can answer all the questions. All right, let me see if I can find somebody else, Jade. And then I come back to you. Nobody wants to volunteer. Jana went already. Guys, please let me go down the list of people here. It's not a school, man. It's for your benefit. All right. Akelia. I hope Akelia can unmute. I hope I'm not butchering your name either. Akelia is not responding. Anthony. Let me try the last name I see here. Or Miss Lynch. Lynch. I'm not really going to say that first name. Lynch. All right, none of the persons beginning with A want to speak. Of course, Abikela went already. Jade, right back to you. Oh, Jade wrote it in the chat. Okay. Let's see. Let me see what's going on in the chat. So Jade has copper 2. Let me write it on the screen for those who are, for the sake of persons who are watching the recording. Trying to move this thing off my screen and it's not moving. Annotate. All right. There we go. So Jade has in the chat copper 2. All right, copper 2 plus ion. What's this? The ion, copper 2 plus ion, gaining 2 electrons. Just write an answer here, you know. Gaining 2 electrons to produce copper solid. Everybody in agreement with that? With this ionic equation?
Yes, sir, I agree.
If you agree, you can raise your hand, please. I appreciate the talking, though. Really appreciate it. Hope you can answer the next question. That was William, though. You're in agreement, raise your hand. 4 persons agree. All right, no problem, no problem. That's good. All right, so we know that copper is being deposited, right? This means that the copper 2 plus ions is being deposited at the cathode, right? The cathode, the cation approaches the cathode and it's being deposited there. Good. All right. Let's see. I can clear my screen real quick because I'll be scrolling. All right. Next question. Calculate the quantity of electricity passes through the copper 2 sulfate when 3.5 amperes of current is flowed for 1 hour. All right, so I see a few hands. I see William and Jade is on a roll. All right. Zario.
Jade is reveal my answer.
Jade is going, no, William, you answer.
Now I'm saying Jade just revealed my answer in the chat.
Oh, Jade, still walk us through it. Still walk us through it. Let us see your process of thinking for those other persons here. Go ahead.
All right.
Mm-hmm.
So
wait, let me get my pen so I can write at the same time. Yeah, ready when you are.
all right. So in order to find quantity of electricity,
Mm-hmm.
it would be I times I, which is amperes, times time.
So Q is equal to I times time, I guess. You're trying to tell me, okay.
And the amperes, which is amperes here is 3.5.
Mm-hmm.
Multiply by how much? Multiply by 60 minutes.
60 minutes, okay. Wait. All right, continue. I'm listening.
All right.
I'm listening.
I'll say times 60 seconds.
All right. What I think is going on here, right? It's all right, guys. We need to know this formula, right? Q is equal to I times T, right? So the easy thing is to plug and play, right? But it's important to know how the formula works. So rightfully acknowledge that this I is amperes, but it should be noted, everyone, saying this publicly, that the T here, like Jay said in the chat, the T here should be in seconds. Right? So we need to convert this hour to seconds. Understand? We need to convert these hours to seconds. So walk me through converting hours to seconds, William. 3,600, yes. So it is 60 times 60. 60, of course we know to convert, right? We know to convert. 60 by 60. And then we can just multiply everything out as one. So we get the answer, 60 by 60.
Yes, sir.
Yeah. I brought attention to this because you didn't bring it to light, right? And that was a little bit worrying because you do all this work, you know the formula. Let me tell you how to mark it. You get 1 mark for the formula, you get 1 mark for the answer. You give the formula, you get 1 mark. You remember this formula, lovely. You get the mark, and then you mess up on the answer part, no mark. 1 mark could have gotten. So it's important to know how to use your formula, guys. This time should be in seconds. All right, so we'll finish with the first section of the paper. Let me see if I can clear my thing. There's somebody in the chat in the thing waiting for me to admit them. Just send them in. All right. Oh, the thing is not clicking. Okay. All right. So let's keep going. In two separate experiments, iron metal and sodium bicarbonate were both treated with excess sulfuric acid, right? The results of both experiments were recorded in the table below, table 2 below. Complete table 2 stating two inferences that can be made from the observation in experiment number 1. All right. So Daniel, I saw you type in the chat. Hope you can chime in here. I'm not sure if you're able to talk or you want to type or what you want to do. But the first observation we made is that when iron and sodium bicarbonate were treated with sulfuric acid, the solution turned pale green. Jana said that there are 2 irons present. All right. All right. So this is actually the answer. Yeah. All right. This is what I love to tell my students. All right. You see, for those who love color, I implore you, come to university and do chemistry. Right? All right. Jada and Jana is on a roll. For those who love color, please come to chemistry. Please come to university, Oak University. Whether it is one in Jamaica or one overseas, and do chemistry. You're going to see color. Where you see at year level, right? At this level, is only a few things have color in your world, right? Of course, you have the transition metals, one's primarily responsible for color. So you have the permanganates, you have the dichromates, you have the iron. What else you have? You have copper. A few things you use, and for those who go in lab, you can acknowledge that there's only a few things you see in there with color. The phenolphthalein, of course, only a few things you see with color, right? So when you say green, guys, when you see green, I want you guys to think iron, right? For the most part, green means there's iron 2 present. You get me? Green means there's iron 2 present. You see the next color. Anybody know the next color that iron can take on? Anybody know the next color?
Orange thing, iron 3 or something.
You're a little bit loud in the background there. Go again. Or you can
Sorry,
talk to
the
the
reddish
chat.
orange or something.
Reddish orange, yes. Reddish orange, that's iron 3, right? That's color for rust. So if it's a green, guys, pale green, anything turning pale green, think iron. If it's a pale green gas, I don't know who knows a pale green gas. You can think like chlorine, or chlorine is a pale green gas at your level. Only a few things have color, guys, I'm telling you. Only a few things. And the mere fact that mention iron here, guys, iron here, and you see green afterwards, right? There's nothing else here that has a color or can have a color. Sodium bicarbonate is actually white. That's baking powder for those who like to cook. Sulfuric acid, for those who have seen it, is colorless. So the whole other thing here, the color is iron. All right, of course, we have to know our qualitative analysis. So we know that if a gas pops, right? If it pops the glowing splint, we know that's hydrogen. If it reignites it, that we know that is oxygen. And if it extinguishes it, we know that is carbon dioxide. All right. Let me clear my screen and move on. State 2 physical properties of iron metal. 2 physical properties. Anybody?
Sir,
Oh, wow,
it
that's a
conducts
lot.
electricity and it's
That's Jade, right?
lustrous. Yes, sir.
Conduct electricity and
It's lustrous.
Lustrous. You might break down that big word for us. I don't think. What does lustrous mean?
Sir, it's shiny.
Shiny. Good. Malleable, solid. All right. So there are a lot of great points in the chat. So you have Jana saying it's malleable, it's ductile, conductor of electricity, high density, high boiling point, high melting point, malleable from Fullerton, right? And of course we heard lustrous and conduct electricity from Jade. All right. Next one, chemical equation for the reaction that occurs between iron and sulfuric acid. William, your hand is up. William, you want to talk me through this?
Oh, no, sorry.
You don't want to talk me through it? Okay. Anybody else want to talk me through this?
Sir,
Yeah, Jay, go ahead. Talk me through it so I can write it. You can write it in the
is
chat
it-
afterwards.
sir, is it 2 moles of iron reacts with H2SO4 to produce Fe2, open bracket SO4, close bracket 3 plus 3 moles of hydrogen gas?
All right, you did a lot there. Before I write that, does everyone know how to construct a chemical equation? All right, if you're unable, if you don't know how to construct a chemical equation, raise your hand, please. So we have Travel, we have Gabriel, we have Nadia. Okay, a few persons here who don't know to construct a chemical equation, right, Jade? So what I want you to do for me, I want you to walk through how you got to constructing that chemical equation, right? Can you do it for me?
Yes, sir. So
Right.
so when an acid and metal reacts, it produces the salt and then the hydrogen gas. So like the salt is when the metal replaces the hydrogen in the thing or something, and then so like that's how I got it, and then it wasn't balanced, so like I put a 3 in front of the hydrogen, and then a 2 in front of the iron, and a 3 in front of the sulfuric acid, and I balanced it.
All right, so first thing first, right? Guys, what JD says that first step, you write the chemical, you write it out. So you know you're adding these two things together, right? Right, guys. And the next thing that JD is saying, thank for the explanation, Jade. Next thing JD was saying is that it's then for you to know, right? Check your notes, check your books. When a metal reacts with when a metal reacts with a acid, it produces the salts, right? But it also produces hydrogen gas. So we can take out hydrogen gas. Easy way to identify the salt. We can take out hydrogen gas. We know hydrogen gas is a diatomic molecule, and we can get the salt. Salt is what sags behind most times, but all right. Important to identify that. All right. Let me see if the question, something guys. Let me see if the question told us what kind of iron. No? Okay. So this is okay, right? You don't have to be all, I don't think it should matter which iron you give them. But I'm choosing here iron. Let me choose iron. Let me choose iron 2. No problem. So the next step here will, as Jade said, which will be to balance. So we identify that there is 1 iron here, 1 iron here, 2 hydrogen here, 2 hydrogen here, SO4 here, SO4 here. All right. So what Jade Jade had to balance because she used iron 2. She used iron 3, sorry. So she made this iron be oxidized, right? She made iron be oxidized up to iron 3 instead of iron 2. So if this is iron 3, that means we need 2 iron here because SO4 is 2, it's 2 negative. You need 2 iron here, you need 3 ions here. Of course, because SO4 is 2 negative, right? I hope, yes, stacing was very important. SO4 is 2 negative, iron is 3 plus. So we can see that if we have the highest common multiple of 3 and 2, we should find something that adds up to 6, right? Let me see if I can join this person. I'm not going to go in much detail about that. Of course, there are videos out there to tell you how to balance polyatomic molecules. I'm just going to why don't you put the 3 on the top? The 3 on the top. Oh, the 3 is not placed on the top because it is telling you how much of this polyatomic molecule is there. If it's placed at the top, it will be a charge, interpreted as a charge. All right, so we identify that there's 1 iron here, 2 irons here, 1 hydrogen, of course, this is balanced, and we have 1 sulfate here, and we have 3 sulfates here. All right, how I normally do it, right? When I'm balancing, guys, not sure how much of you actually, yeah, of course, you have a different ways you were taught, right? Now in high school, this is how I used to balance. I have an XP I want to show you, but I'm not sure how much persons. Isn't it Fe2 plus? Or the thing, Kayla, is that they didn't specify if it's Fe2 plus or if it's Fe3 plus, right? So Jade loves to do work. So Jade chose Fe3 plus because she wants to practice her balancing skills. Yeah. All right. Let me show the easier way. This is how I do it, to be honest, guys. This is how I do it. Up to now, this is how I do it. I'm just going to show you how I do it, and then for those who don't understand, I'll probably go through the next way. So I identified that there's 1 iron here, right? Follow me, guys. There's one iron here. So a little bit of maths involved, but don't worry. 1 iron here, 2 iron here, right? And there is 1 hydrogen, 2 hydrogen here, 1 sulfate here, and 3 sulfates here. Sorry. What I normally do, I'm like, okay, we need 2 irons over here. First thing, we need 2 irons because we have 2 irons here. So I put my 2 irons here. Right? So that is balance. So now we have, how much is this? 3 sulfate ions. So I don't care about hydrogen. I just go put the 3 sulfate ions here. This is how I do it. You can get in trouble sometimes, but you just have to play around the numbers. And then last and not least, there is 3 times 2 is 6 hydrogen here. So you need a 3 here. And this is how I balance it. Everybody follow that? I hope everybody follow that. If you don't follow that, raise your hand. If you don't follow that, raise your hand. It's one person who's not following. Lynch, text me at the end, right? Remind me, make note of this. Text me at the end, and I'll probably refer to like a video or something online. Go ahead.
Yes, sir. I thought you asked who understood what you were doing. Sorry, is my hand. Sorry.
No, I said who. Yeah, no problem. I was asking who's not following. All right. So I hope that clarifies things for Gabriel. I think Gabriel wanna travel. I remember names. All right. Calculate the number of copper deposited. Right. Let's go. Copper number of copper deposited. And when I walk me through that, Lynch, I'm happy that you unmuted. So that means you can speak. I see somebody named Smiley.
Sir, we're still on the same 2021 paper.
Yes, we are.
Sir, I was typing it and I erased it because I thought we changed.
All right, so here it is. So Let me read the question again. The question says, sorry, number of moles of copper deposited. So if we go back to this first page here, number of moles of copper deposited. There's a couple here. So they're saying that, wait, no, wrong part. This is the wrong part, guys. Here, yeah, from here. Number of moles of copper deposited. Yes, so that would be from here. About the total up here, that's total mass of copper deposited was 4.85. The volume was shown in the thing below. Let me see how much marks this is, guys. 1 minute, 3 marks. Calculate the mass of thing deposited given that relative. Yeah, so it's from here. It's from here. What was that? What was our answer to this question? Let me check the chat real quick. So our quality or quantity of electricity was 12,600 coulomb. We can check the chat, or you can check the recording. So the amount of current, the quantity, how much current we put through it, how much electricity we put through the thing was 12,600. I don't know why I keep taking off a 0. 12,600. All right, 12,600 coulombs. So given that we passed 12,600 coulombs through this thing, what they're asking is how much moles of copper was deposited. Anybody? Anybody knows what to do?
Sir, I'm calculating.
You calculate. No, you can't walk us through the calculation in a Jade. Walk us through the
Okay,
calculation.
sir. Sir, one sec.
Let me write something you really need here. Faraday's constant should be, I think it's given as 96500.
Sir,
need this
what I
constant.
did was sorry. Sir, should I answer?
I've been waiting for it to answer, Jade. Everybody's been
Okay,
waiting for it to answer.
sorry. Okay, so from the equation thingy there, like it's 2 moles of electrons or something, and then you multiply that by the constant thing, and then you get like 193,000 coulombs, and then like what you do after that is like divide it by 12,600. You get then you get
Then you get?
Sir, I'm using my calculator.
Oh, I'm looking at the wrong thing.
Okay, so you get 0.6528 moles.
All right. That's a very specific number. I'm not sure if anybody who does not follow Jade. Resign if you don't follow Jade. If you understand what Jade is saying, then don't resign. So one person doesn't understand. Zara doesn't understand. 3 persons don't understand. Don't, D-O-N-T. Don't understand. 6 persons. Okay. What Jade is saying, right? I haven't really checked these numbers yet, right? I was just listening to what she's saying. All right. So let me scroll up real quick. I'll go back to the question. Here, right? The copper in question is copper 2. It's important to identify that it's copper 2 is a thing in question, right? It's a copper 2 solution. Now, remember guys, when electricity passes through this copper 2 solution, the copper 2 plus ions, right? Let me write an equation real quick. The copper 2 plus ions are going to want to do what? Somebody who raised their hand, Zariel, what's copper 2 plus iron want to do? What you going to want to do?
You're going to go to the cathode.
And when it goes to the cathode, what's it going to do in terms of electrons?
Reductions. Yeah.
I didn't get that Jabari.
So the reduction will take place.
Reduction. Okay. So reduction, remember, reduction is a gain of electrons. Right. So it's going to gain it's going to gain 2 electrons, right? And it's going to form a solid. So this is how the copper is deposited. It forms a solid copper. This is solid copper, of course. So that's the first step in identifying what's going on here. If you write this, I think you can get 1 mark, right? Now it's for us to identify that what this Faraday constant means, right? 9,500. What this means is that it takes this much coulombs, so it takes 96,500 coulombs to move 1 mole of electrons or to liberate 1 mole of electrons. So the amount of charge it takes to move a mole of electron, 1 mole of electron is this much. Right? We're following? One person can test it. We're following. We're following, right?
Yes, sir.
All right. So we need this much coulomb to move 1 mole of electron. Right. So how much more of electrons we need? How much moles of electrons do we need to move? Anthony. 1 person. 2 moles of electron. So we can just do my sister showed me this really nice thing she learned the other day. She do it this way, but I'm more mathematically inclined, you see? So I'm just doing this in case I don't want to do it the way I do it and make it jump over in the body head. So this is what she did when I explained to her. She did 96,500 and she said this goes towards 1. I'm not sure how much persons, that's still a few persons who do it this way. All right. And what I'm saying is, what you're saying is that you need 12,600. You want to find out how much moles of electron 12,600 goes towards. 12,600. So this goes towards, I guess, X. There are a lot of ways you can do this. It's very surprising. I'm trying to draw this thing. Don't want to draw. Please draw. It goes towards X. And she did this thing where she cross multiply. And she ended up with 96,500 X equal. Everybody following?
Yes, I'm following.
You guess you're following? Or where I lose you?
No, so I said I'm following.
I heard I guess I'm following, that's what I heard. So I was just questioning your uncertainty or apparent uncertainty. And then she just solved for X. So she said X is equal to this number on the right divided by the number on the left. This is equal to 12,600 divided by 96,500. 96,500. I believe that should be the same answer you got. Jade, was the same answer you got?
Sir.
All right. Remember the number, please. 0.8. How do you get the 1-to-1 ratio? Hernandez, sorry. Hernandez, go ahead. Repeat. I don't understand the question. Hernandez. I don't think I understand the question, Hernandez. All right, so I'm not hearing Hernandez. But if you don't follow, raise your hand. Gabriel is not following. Gabriel, where do you not follow? Gabriel? I'm not hearing Gabriel. I'm going to think that, oh, you got cut off. Okay, go ahead. Unmute your mic and go ahead.
Sorry to interrupt you, but 12,600 divided by 96,500 is not the final answer, right, sir?
That is a final answer.
But sir, so wouldn't you have to divide that by a half to get the number of moles of copper deposited based on the mole ratio?
All right. Let me walk through this again. This to 1. This goes to. Oh yes, this is supposed to 2x. Sorry, thank you.
You're welcome, sir.
All right, thank you. All right. So divide this by 2. Oh, I got the 96,500. The 96,500 is a Faraday constant. Let me double check through this procedure once more. Let me double check through this procedure. Jay, do you have a question?
Sir, wouldn't you multiply thingy there by 2 since you have 2 moles of the electrons or something?
Yeah, give me a minute. I'm double checking through what Gabriel just told me. So you have this goes to 1, this goes to x, right? All right. How much moles would this liberate? So this will liberate this much moles of electron. If it liberates this much moles of electron, you have to divide it by 2. Jade, the reason we have to divide it by 2 is this liberates let me put 2x right here, so it should be 2x. The reason why you divide is because, let me see if I can find an analogy for you. If a boy, right? If I have a boy here, right? Let me see if I can draw a boy here. And he needs 2 pizza or 2 slices of pizza to be filled. I think that's too abstract for you. I think that's too abstract. We do not understand it that way. Okay. Let me do it next way then. Let me do the next way. Equal 1 more pizza, therefore Yep. So John has the same thing as I just did in the chat. Jana, but you have to divide it by 2 at the end. So Sean, Miss Hall, is it that you don't understand everything, or you don't understand why we're dividing by 2?
Sir, I don't understand why.
You don't understand? Oh, you don't understand? Repeat that. You don't understand what? You don't understand what I heard the first time is that you don't understand why there's a 96,500.
No, sir, the ratio.
The ratio. Okay. Okay. Let me walk you through it then, because
Excuse me, Alex.
mm-hmm.
Sir. You'd have to, I think it's because you put the 2 and divide by 2 instead of multiplying in the first place. So you put back the 2x, 12,600 to 2x. They multiply 96,500 by 2 and write x afterwards. So it would be 96,500x. Yeah. Toya put it in the
Sure.
chat. Fine.
Yeah.
Sir, I had a question.
Go ahead. Question.
Sir, what I was asking, like if you would like multiply Faraday's constant by 2, since you have 2 moles of electrons, and then like divide it or something by something. I don't know.
All right. So let me see if it works that way. Let me see if I can get my calculator. And see if
Sir,
it
what I
works that way.
did was multiply it by 2, then I divide, like I had a division with the thing I got before in the previous question or something.
All right. So you multiply it by that. Yeah. You get the same answer. What answer did you get, Jada? Jada or Jade? Jade, what answer did you get?
Sir, I got 0.6528.
0.65 or 0.065?
Oops. Yeah, 0. Sorry.
All right. So we're all getting the same answer, right? It came down, yeah, if you understand it that way, Carl, then wonderful, you got the answer. But the way I was showing it was an alternative method, right? I just so happen to, you can either put the 2 here and you do the maths from here, or you can just do it and then divide by 2 at the end. If you really understand what's going on with the moles and whatever. Everybody's following? Who is not following? If you're not following, raise your hand. Okay, I think everyone is following. All right, calculate the, so, Bailey.
Okay, so it's not that I'm not following, it's just that I don't understand the moles of concept, like the concepts of moles.
We'll get to it. We'll get to it. We'll get to it. We'll get to it, trust me. If I don't see a question addressing it head on, we'll get to it. I think next paper should have some next paper should have some titrations and stuff. So trust me, we'll get to it. All right, calculate the mass of copper deposited, given that atomic mass of copper is 64. All right, anybody want to walk me through this? What we do first? What do we do?
Sir, you multiply the number of moles by the relative atomic mass.
All right, so the number of moles we had was 0.65. Why are you multiplying by atomic mass again?
Sir, to get the answer.
Why are you multiplying? Oh my lord! What's the formula you're using? Is there a procedure you're using? Is there a formula you're using? Why are you multiplying?
No, sir, I just multiply the relative atomic mass by the number of moles to get the mass. Sir, like
right.
to get the number of, like the mass of the moles, like you have, like you just multiply the thing and then you get the answer.
I really wanted it to identify the formula. I really want it. Okay, it centers around the formula. It's so wonderful.
Sir, number
So
of moles equals relative atomic mass times the number of moles deposited or something. I don't know.
As in mass equal molecular
Their mass is
times the
equal
number of
moles
moles.
times relative atomic mass.
Yeah. So it's good that you acknowledge that formula. I really wanted to acknowledge that formula because persons can be there wondering, why should multiply this by that? Right? So that formula she mentioned about the mass being relative molecular times moles, it derives from this root formula. Moles equal to mass over molar mass. So of course you're going to multiply, you transpose whatever gymnastics you're doing, you get 0.65 times the mass, times the molar mass, sorry. Repeat, somebody tell me the answer, please. Can I write it here?
So 4.16.
4.16.
Grams, sir.
Thank you for the grams. I appreciate that's Jabari, right?
Yes, sir.
Yeah. See, guys, at this level, they don't really pick you for like not missing off grams and stuff. But as you get higher, important. Keen iron units and stuff. All right, so just one reason for difference in mass calculated in B3 and the mass measured by the student. So why is there a difference here and a difference? Yeah, go ahead.
Sir, perhaps when the electrode thingy there was being removed from the electrolyte, like the student didn't like dry it off or something, so the water like added to the mass or something.
Repeat that again.
Sir, when the thing was being removed from like the electrolyte, like probably it wasn't like dried off or something, so it like the weight of whatever it was in just contributed to the mass or something. No.
It wasn't dried off, so the weight is why? All right, so the weight measured by students is higher than the weight calculated here. You're saying it wasn't dry?
Yes, sir, because it was in the electrolyte thing. I don't know.
The closest thing I can think to your answer is perhaps when the person collected it, the copper itself wasn't dry. That's the closest thing that I don't think I'm understanding what you're saying.
It was wet, so the wetness made it heavy or something.
Okay. All right. Okay. Fair enough. So that would be an error, right? So you can of course say that and say that was a personal error, or I don't what terminology you use now. Personal error. I think personal error is what you use. You're familiar with the term personal error, right?
I don't know, sir.
No? Okay. What are the errors you know? I know you know syntax errors, parallax errors. What other errors are there?
I don't know.
You all know. Repeat that.
So systematic or instrument error?
Systematic instrumental. Parallax would be on the yeah. So what I'm saying is similar to parallax error. What she's saying is parallax error. So parallax would be it's on your end, you're doing something wrong. So that could be a reason why. That could be a reason why. So we're seeing here the theoretical thing is different from the actual obtained thing. So it could be on the end of the student.
So it could also be due to impurities present in the copper.
That would not be a answer. Reason being, electrolysis is used to refine copper, right? So whatever copper is formed on that electrolyte, on that electrode, whatever copper is formed on that would be pure copper. So there would be no impurities there. All right?
Sure.
Mm-hmm.
So could an answer be like the balance that it was being weighed on was not zeroed or something?
You could say that as well. You could say that. Are there potential errors in the system? Are there potential errors in the methodology used by the student? Did I highlight what the student did? This is the theoretical thing, right? Pass through for an hour. It could be that the student, or the student did for an hour. Yeah, there's nothing wrong with the. I see nothing wrong with the method used, right? All those answers you're blaming the student. Essentially, you're blaming the student for what the student could have possibly done wrong. There is nothing else there. All right. Let's see what else is here. So state the color change that would have happened in electrolyte or after a few hours. What color change would happen, guys?
Or it would become like colorless or something. I don't know.
Blue
What
to
color is it coming
colorless.
from?
It's becoming from blue to colorless or something.
Blue to colorless, yeah. Copper 2+ is blue, guys. So it as the copper is depleted, right? Sulfate is colorless. Remember sulfuric acid, H2SO4 is colorless. So as the copper 2+ is depleted, of course, there's less blue things that's blue in there, so it's less blue, so it's going towards colorless. All right, the student was asked to use the same electrolyte to purify a piece of impure copper. Now state how the electrodes in figure 1 can be modified to obtain pure copper from impure copper. What would you do?
Sir, make the cathode pure copper and the anode use the impure one.
Okay, I'm trying to load the screen so persons can see. So you're saying make the cathode pure copper, right?
I think
the cathode,
so. I think so.
pure copper. I made the anode impure copper.
I think so.
Why did you do that? Why would you do that?
Because like one of them is gonna like dissolve or something in the solution or something, and then like yeah.
All right, so true, one of them is going to dissolve in the solution. Recall that the cathode, what goes to the cathode?
Sir, the copper thing goes to the cathode.
The cations go to the cathode, right? So an easy way to remember this, guys, an easy way to think about it is the side what the cathode is going, the side of the copper is going to. You don't want the copper to be deposited on dirty copper. That makes sense, everybody?
No, sir.
No?
Doesn't make sense to have it deposited on impure copper or something.
Yeah,
I
that's
agree
what I'm
with
saying.
you, sir.
Yeah. Everybody's following?
I'm sure I can explain.
All right. So are you familiar with refining of copper where one of the side gets small and one side gets a buildup of copper?
Yes, sir.
All right. What I'm saying is to identify which side you put the pure copper and the impure copper on. What I'm saying is that you should identify that the cathode, right? The cathode, the cations go to the cathode. So cations would include the copper 2+, the H+, those things go to the cathode, right? And when they go to the cathode, the copper will become solid. So you would, if you want pure copper, right? You're refining the copper, you want pure copper. You're going to want a clean piece of copper here at the cathode, so that whatever buildup occurs on that copper, it's not made impure. Basically, you don't want to make the copper dirty. You know what I'm saying?
Yes, sir.
You want a clean piece here, so when the copper comes over here, it adds on to the clean piece. If there was a dirty piece here, right, the same thing would happen. If there was a dirty piece here, the clean piece on the next piece would come over, the clean copper would come over on the dirty copper. And everything would be dirty. Let me pause. I can't mute Fagan. Fagan, can you move for a minute, please? Background is kind of loud. All right, so this thing is taking its own sweet time. Let's see if I can download this. All right, let's move on. So of course we say that the anode will be the impure copper And the cathode will be the pure copper. All right. Acids react with bases to form base. Acid reacts with metal and bases to form salts, right? John conducted experiments to investigate the properties and the reactions of acid using, it should be, using sulfuric acid and bicarbonate, sodium bicarbonate, and iron, right? So John conducted experiments to investigate the properties of acids using sulfuric acid, iron, and bicarbonate. Define the following term. What's an acid?
Sir,
Mhm.
sir, an acid is like a thing that like when it's dissolved in water, it ionizes or something to produce hydrogen or something.
So
Like an ion.
instead of saying something,
ion.
right? I noticed that you like saying something. You like stuff. Very big. You like something and you like stuff, and what else you say, like something, stuff. Those are the two things that I noticed you like did. So instead of saying something, you can describe that something. How would you describe that something?
An acid contains H plus ions.
Acid contains H plus ions.
Sir.
So water can contain H plus ion. Is water an acid?
No.
All right. So what's an acid, Hall? Like in the definition, Gabriel.
Gabriel, sir.
Gabriel. Oh, yes. Like the angel. All right, Mr. David. Travis.
Sir, aren't there multiple definitions for acid?
Yeah, there is. I was looking for you to describe your something. I don't want to go on the paper and write something. Whatever you practice, going to write. Let me give you a word. You can say substance. You can find other words, of course, but I want you, Jade, to find words to describe your something and your stuff. And I can spell substance now. Substance. My lord.
Sir.
Travis, go ahead.
Since it's one more, can I say acid a proton donor?
You can say that, definitely. There are multiple definitions. Multiple. Proton donor, lone pair acceptor, something that ionizes to substance which ionizes. I'm writing this one because this is the first one I got. I probably shouldn't write it because it's the longest one too. Substance containing hydrogen, which can be replaced or directly, Substance containing hydrogen, which can be replaced directly or indirectly by a metal to form salt. I mean, I guess that's okay. I'm trying to think about any other chemistry I know where there is a substance with hydrogen where it can be replaced to form a salt. That's what I'm trying to find. Jaden. No, I think you're all right. I think that's okay. It's very specific though. I think it's okay though. Substance that dissolves in water to liberate. Yes, Jana. That's exactly what I'm writing. But I'm writing it in a watered-down form. Jana, that definition is wonderful. Acid is a substance that dissolves in water. Watch your grammar. Dissolves in water, liberates H plus ions as its only positive ion. Okay. As its only positive ion is, you don't really need that part, but you can fix up that part. But it dissolves in the water or, let's not even say dissolve. It dissociates in water to liberate H plus. So I can say ionize. There's so many ways you can say. All right, so in the meantime, what's a salt, guys? I think Hall raised their hand. Oh, no, it's Edwards. Edwards, go ahead.
Sir, a salt is a compound formed when some or all of the hydrogen ions in an acid is replaced by metal ions or ammonium.
All right, wait a minute. Let me finish write this first. I was ready for that bombardment piece. H plus. All right, go ahead. Sorry about that, Edwards.
It's a compound. A salt is a compound that's formed when some or all of the hydrogen ions in the acid are replaced by metal or ammonium ions.
All right, so when the hydrogen ions are replaced by metal or ammonium ions. That's what you're saying?
Yes.
Yeah, that's okay. Everybody agree with that definition?
Yes, sir.
Yeah. Everybody following that? Everybody who does not follow that definition? So everybody follows the definition. Okay, wonderful. I love doing explaining. Hydroxide is a substance that dissociates in water and liberates hydroxide ions. Hydroxide dissociates in water and liberates itself. Okay. All right. Next question. John dissolves bicarbonate in water, tested the solution with red and blue litmus paper. Red litmus paper turned blue, blue litmus paper did not change color. State one reason, or base. State one reason. We didn't ask for base, Kimani, but yeah. Or you can say something that reacts with acid to form salt and water. You can say that as well. Okay. Salt? No, that's not a definition. I don't think that's a definition. Not all salts dissolve in water and produces hydroxide. Sorry. So I read this already. State one reason why red litmus paper turned blue and why blue litmus paper did not change color.
Sure, because it's an alkaline, and in alkaline, it will turn the red blue, but it won't change the color of the blue paper because it's alkaline.
Yes. Everybody following that definition? Everybody understand? Or who does not understand, I guess?
Yes, sir.
Travis, you do not understand?
No, sir, I understand.
Okay. I was asking who did not understand. That's generally a smaller subgroup, sorry. All right, so Travis, while you're here, right? State whether the pH of the bicarbonate will fall in the range greater than 7.
Yes.
Oh my Lord, Travis, you change your name to Jade. Jade, you're answering all the questions.
Sorry, sir.
I mean, I want to go on the paper and answer all the questions, yeah, but I wanted somebody else to. I want to see if Travis knows what he was talking about. All right, I think this thing is. I should have downloaded these papers, you know. All right, so we'll finish with that part. We're going to organic. Organic is lovely. 2 organic molecules, A and B, have the following formula, right? Let me read it to you. C3H8 for the first one and C4H8. Write the general formula for the homologous group in which compound A belongs. First of all, what's the homologous group of compound A?
Alkane.
Alkane. Okay, wonderful. Does anybody know the formula for the alkanes?
CnH2n plus 2.
CnH2n. Yes. All right. So there's not much to say there. You just have to know that formula. Just have to know that formula. Oh, something like this came when I was doing CXC as well. It's interesting. All right. List 3 general characteristics of a homologous group. We don't normally say this in university. Don't mind me. We normally say functional group, or we don't really use this word. But people can bash and say functional group is not the same thing, but just me. Name 3 general characteristics of a homologous group other than the general formula. William.
All right, so they have similar chemical properties.
Mm-hmm.
Next, they have the same functional group as 2. And then last one, they all have the same general formula.
Other than the general formula, William.
Other than general formula?
Mm-hmm.
So that's the only thing, that's the only 3 things I know.
Powell looks like she wants to help you. Powell, Naomi.
Yes, they have the same decimal properties and all can be prepared the same way.
Decimal properties, mind elaborating?
Sorry, why am I saying decimal? I mean chemical, but well, he already said that, but they can all be prepared in the same way.
Okay, so they have similar mechanism by which they can be prepared. Okay, not with that one actually. Jana.
So the member before and the member after differ successively by a CH2 group.
Wait. Repeat. Slow down.
The member before and the member after in a specific homologous series differ only by a CH2 group.
That's not true for all of them. Is it? I think it's true for all of them. Alkanes, alkenes, alcohols, alkynes, thiols. Okay. All right. I can get behind that. A little bit question mark there for me personally, but I can get behind that. Different empirical formulas. Is that a characteristic of the homologous group though? Homologous series though? Jana? Same formula?
Mostly I was responding to the question in the chat.
Oh, okay. No, it's a different empirical formula. Empirical formula is a small one. Yeah, it's a different empirical formula. All right. Are there any other? So you're saying that across the entire CXC, across the entire Caribbean, those are the only responses that they'll be able to see, that they'll be able to mark correct? Anybody else?
Like there's a trend like in this thing when the amount of carbon that increases, like an increase of like boiling or melting points. I don't know.
I think reactivity decreases as the carbon count increases.
Reactivity decreases as the carbon count increases. Okay.
So
all right, I think.
Sir, and for some of them, like carboxylic acid and alcohol, the solubility, like I think the solubility, like something happens with the solubility.
It decreases as they get bigger. For the carboxylic acids, alcohols, questionable. They don't always decrease. Is there a general trend for decrease in alcohols? Yeah, I think alcohols probably decrease as well. All right. I think you guys cover all the bases. Don't think too hard, right? Just give answers you're confident in. All right. Identify the homologous series in which compound B belongs.
Alkenes.
Alkene.
Compound B is C4H8. So who says alkene? Alkene. Anybody say alkene? Anybody think it's an alkene? I think it's an alkene. Anybody agree with me?
No, sir.
No, sir.
Paul, you agree with me?
Yes, sir.
You agree it's an alkene? Why do you think it's an alkene? Defend me for me. Defend it for me.
Wait, sir, you said you think it's an alkane?
Yeah, alkane, A-N-E.
Sir, I don't think so.
You don't think it's an alkane?
Compound B?
Yeah, compound B.
No, I don't think it's an alkane because the formula doesn't reflect that. The formula.
Okay, no problem. So justify that. Tell me how to draw compound B. Powell?
Oh, okay, how to draw it?
We're drawing it for the next answer.
Okay, well, we're going to draw 4 C's.
All right, I'll draw 4 C's. Don't matter how I draw it, don't it?
Well, what would it, the chain, the single bond? Draw a single bond, 4 single bonds.
You're supposed to have a double bond.
There's supposed to be a double bond there.
You said 4 single bonds. Double bonds anywhere? Okay, I'll put it there.
You should have a, okay, yeah.
I should have a what? Repeat.
I was going to say you should have a carbon double bond.
Okay, no problem. Anything else, guys?
And then each carbon has 2 hydrogen single bonds.
Every carbon have 2 hydrogen. So you have
Same.
2 carbon, 2 hydrogens around this as well. This middle one there, it should have 2. This one should have 2 hydrogens as well.
You'd have to put.
This has 2 hydrogen.
You'd have to put the that carbon as a single bond to the last carbon.
Wait. You're saying that this carbon here should have 2 hydrogens?
Sure, the carbon doesn't have any hydrogen at all.
You wouldn't have any hydrogens at all? Okay, let me undo that. Okay, undo. And the reason I'm asking all these questions, is I really want to see the procedure by which you draw your things, right? Nothing is wrong with drawing this way. You know it has a double bond. Nothing is wrong with doing that. All right, but for those who probably get the first one wrong, right? I don't see why you should get the first one wrong. Normally, when you're drawing things like that, they tell you to draw all the single bonds first. Connect all the carbons. You know it's connected, right? Let me 1, 2, 3, 4, 5, 6. Of course, you're missing a hydrogen here. This is the problem. Missing a hydrogen here, we're missing a hydrogen here. Let me admit this person. So this is the complete thing. Of course, guys, put in your carbons, please. Please put in your carbons. And you don't leave it empty like this. Put in the carbon so you don't have any wrong example. Things that I want to draw. Please draw.
Excuse me, sir.
Go ahead.
Wouldn't this compound not be the one stated, but the isomer of that compound due to the straight?
I mean,
1, 2, 3 right there.
Did they specify it was supposed to be a straight chain, Jabari?
I mean, this said draw compound B.
Yeah, they said draw compound B, but when you look at the formula, did the formula say it's supposed to be a straight chain? The formula didn't say it's supposed to be a straight chain. The formula doesn't tell you that. Isomers have the same formula. They just have different structure. You have different type of isomers. But the one we're looking at now is conformational isomers. I think that's what you're doing at this level. Conformational isomers. So they don't have a different formula unit. So it doesn't matter. Good question though. Hall question. I don't know nothing at all in organic chemistry. You have to read Hall. I can. But take time to go through organic chemistry. We're gonna take today and tomorrow and the day after that.
Excuse me, sir.
Sir, which year paper is this?
2021, same way. We're almost finished though. Halfway through. All right. So compound A, let me show you how I draw it. So we all drew this together. So compound A, when I'm drawing a thing, right? Carbon, my thing is lagging. Okay, I draw the carbons first, right? And then I say, okay, I have 4 carbons. How much hydrogens do I have? I have 4 times 2 plus 2 is 4 times 2 is 8 plus 2 is 10. So I draw my 10 carbons. How much bonds can each carbon accommodate at any given time? Everybody can unmute it to me. 4. So I try to make sure that I have 4 around each carbon. Make sense?
Yes, sir.
Make sense? So I have 4 here, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So that's the methodology I use. And of course, filling the hydrogens, I'm not doing that right now. Filling the hydrogens. So if I use that same methodology with compound B, right? Let's say instead of guessing and saying, oh, this first one should have a what do you call that? What did I say? You should have 2 hydrogens here or not. I think Jabari was the one. I don't think it was Jabari. Somebody was telling me about this thing having two hydrogens. So if I use the same analogy here, I know I'm supposed to have 8 hydrogens in all. So I just make sure everything has 4. So this has 1. So I say 1, 2, 3, 4. You're good. This has 1, 2, 3. I can put 1 here. Look how it works. So this has 1. I can put this is 1, 2, 3, 4, 5. So I can put 3 more. 1, 2, 3, 4, 5. That's 5 hydrogens. So I can put 3 more. So this is 6, 7. Okay, I mean I have 2 hydrogens left, so I can put 2 hydrogens here. But the following, I think everybody's following. I put the 2 hydrogens here. I have 8 hydrogens, but I realize that this carbon is not very happy, so I can put a double bond here, right? So that's the next way you can think about constructing the formula unit, the structural thing, right? Let me see. Next question. Almost done. I want to finish this by 12, you know. And hopefully go on to the next question, next paper, and finish that. Hopefully we can go faster the next paper, guys. Describe a test to confirm for the identity of carbon dioxide in experiment 2. Include your expected observation. So how do we test for carbon dioxide? Anybody?
It's in lime water.
With bubble gas through lime water.
Wait, one person. JD, you're talking?
So I was saying lime water, and then if a milky white thingy there is formed, it's present.
So describe the test to me.
Sir, you bubble the gas thingy there through lime water, and then if you see a milky white, like a suspension thingy, it will indicate that it is present.
All right, so you bubble it through the lime water. I heard lime water. I didn't hear the bubble part first. So I was wondering if you just get lime water and you just change color. So you bubble it through the lime water. The observation would be it would expect the term white, milky white. The next person was talking. There are other tests. I think there's one more test. Another person. Nobody. Give me a test for oxygen.
A glowing splint. You'll relight a glowing splint.
All right. So if oxygen promotes combustion, yeah?
Yes, it does.
All right. Firefighters, if they don't use
Sorry,
foam.
isn't it going to be extinguished?
Extinguished, thank you.
I think oxygen relights the splint.
Yeah, oxygen reignites the glowing splint.
So does it extinguish it or something?
Yes, it does.
I don't know.
Yes, it does. That's the next test I was trying to get from you. So that's the answer. There are two answers you can have. glowing splint, or you can have the milky water. All right. Balance equation including state symbols for the complete reaction between sodium bicarbonate and sulfuric acid. Somebody walk me through this quickly. Let me see what's going on here. Of course, we know to write this up. Somebody please put that in the chat. Put what exactly, Lynch? Be specific.
So what it is for oxygen and what it is for carbon dioxide.
Oh, oxygen reignites the splint. You know, oxygen, you need oxygen to have a fire?
Yes, sir.
Yeah, so you would reignite the splint, whereas the carbon dioxide would extinguish the splint. How will we get this recording? It will be made available to you afterwards. Trust me. I'm not the person doing technicalities and stuff like that, but it'll be made available to you. Right. All right. So that being said, we're adding these things. You're adding these two things together, right, guys? We're adding these two things together. What do we get at the end?
Sodium sulfate, carbon dioxide, and water.
Sodium sulfate, carbon dioxide, water. Okay, draw the arrow. Anybody know why we get those things?
Because a carbonate reacting with an acid will give salt, water, and carbon dioxide.
Yes. Well done. Someone was saying something? I thought someone was saying something. All right. And carbon dioxide, is it balanced quickly?
No.
No, sir.
Tell them what to do.
Put 2 in front of the sodium bicarbonate.
Repeat.
Put 2 in front of the sodium bicarbonate.
Put a 2 in front of here. I'm trusting you guys now. I'll check afterwards. Put a 2 there.
Put 2 in front of water and carbon dioxide or something.
2 in front of water and 2 in front of carbon dioxide. All right, give me a minute.
I said 2, sir, 2.
2 here.
Yes, sir. 2.
And 2 were here. Is that
Yeah,
everything?
I think so. I'm not sure.
Is that everything, guys? What
No,
about the
sir.
state symbols? What about the state symbols? Accurate. Wait, somebody said no, that's not everything. What else should be there?
Oh wait, sir, I thought the hydrogens weren't balanced, but I think they're balanced.
Or what is, everybody remember the solubility rules?
Yes, sir.
So what's the solubility of sodium bicarbonate?
Aqueous.
I think it's insoluble or something.
Sodium bicarbonate is insoluble?
I'm not sure.
It's aqueous.
I think it's aqueous.
It's aqueous actually. Revisit your solubility rules, please.
So that would be because it's a carbonate of a group 1 metal.
Yes.
Okay, sir.
That's explanation I give you at this level. Trust me. If you want to learn more, come to university and do chemistry. No, they're not paying me for it. It's not advertisement. Sodium sulfate. Sodium sulfate. It's soluble, insoluble. Guys,
Sir, it should be soluble.
soluble. Okay, good. Is it balanced? No. Okay. Is it balanced, guys?
So I'm not seeing the screen.
No.
So I'm saying I'm not seeing the screen.
H2.
Sir, I'm not seeing this.
4. Oh. Are you
Sir,
hearing me,
the
guys?
screen is not visible.
Or you see, there's lagging. able to guys. One breaking.
Sir, the screen is black and it's not, can't hear properly.
Can you hear me? Oh, I'm lagging. Okay. All right, give me a minute. Let me see if I can. What's going on with computer? Are you overheating? No. Let me put this up here. Hello, are you hearing me now? All right, so this thing is up here. No way. Okay, you're hearing me? Trying to stop sharing the resume. Yeah, I'm doing that right now. I'm also quitting a few things on my computer. So hopefully that works. I think it's a memory issue. Are you hearing me now? Is it less choppy or whatever?
I can see it now.
You can see it as well?
Yep.
Sure, I can see it. All right, you can hear, you can see. Actually, let me try turning off my camera. Sometimes the bandwidth thing happens and whatever. Is it better? Is it smoother? Better. Okay, no problem. All right, in that sense, is it balanced? I was checking course balance. Okay. This is for carbon dioxide. This is CO3. Okay. H2CO3.
No, it's not balanced yet.
What else needs to happen there, Jabari? Wait, was it Jabari or was it Ricardo? Ricardo, were you talking?
Oh no, it's me, Gabriel.
Oh, Gabriel. Why is it not balanced? Talk to me.
The oxygen on the other side, it adds up to 8, I think. 4, 6, 10. It adds up to 10.
All right. So let me go through the balancing act that was attempted here. Let me see if I can get my eraser. Erase this 2. Erase this 2 right here. Erase this 2 right here. Okay, let me see if I can balance this real quick. I'll help you guys out with
Wait,
this.
sir, is it CO3 at the bicarbonate?
Yeah, it's just bicarbonate, it's a CO3.
I couldn't see that properly.
Was it balanced? Bennett, Jana.
Yes, sir.
You had your hand up?
No, sir.
Okay. 2 carbons are 2 sodiums, H4, 4, 4. Okay. CO3, you have 1 C, you have 2 C's. You need 2 C's here. You have 4 oxygen here. You have 6. And you don't have 4. You have 4 plus 2 is 6. You have 6 up here, so 3 times 2 is 6. Sulfur. It was balanced before. Was it Gabriel? It was balanced before.
Sir?
All right. It was balanced before. Before I removed the 2's and whatever, it was balanced.
Okay.
All right. Let me see if I can move on to the next question very quickly. This lagging thing is getting to me. All right, let's see. Inorganic. So modern periodic table arranged such a way that they're grouped in terms of the chemical properties they exhibit. Many of the elements exist in a mixture of isotopes. All right, so table 1 shows symbols of selected elements in the periodic table. State the configuration of silicon and justify its position in period 3 of the periodic table. Anybody? You can send it in the chat, you can say it out loud. Send it in the chat as well.
Sir, the electronic configuration is 284 and it is in period 3 because it has 3 shells.
Period 3.
It
cells.
has
Okay.
3 shells or
Yes,
something.
lovely. That's Jade, noted. I know it's Jade because she said something. My Lord Jade. I'm begging you, don't write something on the paper. But your answer is correct. So it's in period 3 because it has 3 shells. All right, guys. Remember 3. Yeah.
So you say when the more when you count the shells, you find the period.
You count the shell for a period and you look at the valence electrons for the group. Get that, Richie?
Yes, sir. Yes, sir.
All right. Of course, it will be in your notes. You can double check on that. All right. The sample of group compound A is placed in a test tube. Sample of compound B is also placed in a test tube. As applied potassium permanganate is placed in each test tube. What expects to happen in test tube A? Test tube 1 was an alkane. No, test tube 1 was an alkene. Test tube 2 was an alkane. Was it that way? I think it was.
Is test tube 1 an alkane?
Test tube 1 was an yeah, test tube 1 was an alkane and test tube 2 was an alkene. Oh, that means we drew the wrong thing here. This was supposed to be C3H8, not C4H10. But okay. Or whatever. All right, yeah. So an alkane, how does an alkane react with potassium permanganate? With aspide permanganate?
So the test tube 1 is an alkane.
All right, one person. The alkane will do what? So let's say we know what the alkane is. We know what the alkane is. Alkene is. Test tube 1 was the Test tube 1 was the alkene.
Sure, I think it was alkane.
C3. Yeah, alkane. Yeah, because C3H H8. So the alkane was here. How does the alkane react with the
Sure, the purple color is gonna persist unless like there is ultraviolet light present.
Okay. So the purple color persists, right? Everybody, you should just know that because it's in notes, right? So what about the alkene?
Sir, it will become decolorized.
It will decolorize. From purple to colorless. From purple to colorless. I want to tell you something so badly, but I don't know. Like, I don't know how. I don't know. Oh my Lord. All right, let me tell you the same way. The reason why I was going to tell you the reason why I changed from purple to colorless. Not really on the syllabus. I think we have time. The reason I changed from purple to colorless is because it's oxidized. It's oxidized and double bond is broken. So the color changes. So it changes from a alkene to an alkane. And that process of oxidizing gets rid of some of that permanganate and lovely stuff. I'm really trying to tell this subject to you, huh?
Oh,
Sir,
because
I think
permanganate solution is a reducing agent.
It's but it oxidizes the thing. Wait, 1 minute.
The
Sir, I
reducing
think my
agent.
teacher said it or something like that.
1 minute. Potassium permanganate. It's
an oxidizing agent.
It's an oxidizing agent, sir. Potassium permanganate is potassium manganese 7. Manganese 7, MKMN 7. Who's coming in the group? 7 plus. So there's nothing above it. It's an oxidizing agent. I was about to justify why it was the oxidized agent. So this form of manganese is purple. So whenever it interacts with anything and turns colorless, it normally turns to manganese 4. Manganese 4 is colorless. But it's oxidizing agent, trust me.
Sir,
Reads up
which
here,
one
you know.
turns pink?
It pink?
Sir, which one turns pink? I heard of
Which
one
man
turning pink or something.
or which manganese turns pink?
Sir, one of them turns pink. I don't know which one. Which one was it?
Probably manganese 5. I'm not really too sure which one turns pink. And I can always calculate it, but it's a lot of calculation. But I think probably 5 turns pink. I'm guessing there as well. You can always look it up. Of course, you won't be tested on this, so for those who are wondering, oh, we're supposed to know if it's supposed to be pink. No, you're not supposed to know that. Next question. So we know that alkanes, in the presence of alkanes, the color persists. In the presence of alkenes, the color changes to colorless. All right, state whether compound B is an alkene. Is it saturated or unsaturated?
Sure, compound B, I think it's unsaturated or something.
Unsaturated. All right. We're still at 2021, Richie. Almost done. This is the last word paper. So it's unsaturated. So give one use of the following compound. One use of compound A. Compound A was
Propane.
C3H8. Propane, yes. One use of propane.
For fuel in stove.
Fuel in stove, okay. And compound B was C4H8.
Butane, I think.
Yep. Mm-hmm.
Sure, can it be used in polymerization?
You can use in polymerization, definitely. Never seen somebody use, I never heard it in the pop one with butane, but next one.
Can it be cracked or something?
It can be?
Can it be cracked? I'm asking if it can be cracked or something.
Yeah, definitely can be cracked.
So it can be cracked to make something that can be used to make a polymer or fuel?
All right. All right, so you see cracking now, cracking is kind of uncontrolled in a sense. You get me? When you apply heat to it, you can't really tell it exactly where you want it to break. So that answers, even though it's an answer, it's not really the soundest of answers. Understand?
Yes,
answer you had before was a better answer. All right, let me see if I can flip this on the side. I think I might have to download it if I want to do that. Pop out. All right. Are you still seeing my screen?
Yes, sir.
All right. I'm just downloading something real quick. Downloading this real quick so I can flip the thing for you. All right. So let me see if I can share. Admit this person. We're 48 persons presently here. I'm going to share at next up occupation. I have the thing open. Okay, it's going through. We're all the way down here. Here. Click this. All right. So compound carbon, hydrocarbon in C3 should be here. C3. Where's C? ABC. I think something's going on here. A, this is D. Okay. Okay. 5. Carbon in C3 is allowed to react with bromine in the presence of sunlight. Draw structural formula of the monobromo compound form. Oh, okay. So it's probably the alkene. Sunlight, it's probably the alkene. So let me see if it's alkene. C3. 1, 2, 3. Here's C3. All right, guys. It's an alkene. I just can't find C3 at the moment. So I can't find C3. It's alkene. And it's alkene. How would I draw the monobromo compound form? How would I draw that?
Sure, you'd have the 4 carbons, and then instead of like one of the hydrogen, instead of having that there, you'd have a bromine. So you'd have like all of the hydrogen except one is a bromine.
All right, everybody following that? Because a monobromide. Okay, no problem. All right, of course, you just have one being a bromine. Right. All right. States the type of reaction that occurs between the alkane C4H10 here and the bromine.
Substitution.
Substitution reaction. Everybody agree with that?
We also say halogenation.
I was about to say halogenation, you know, but I wasn't sure if you guys was familiar with that term. Halogenation.
Yes, sir.
Halogenation
Familiar with the term.
or substitution should be all right. Or you can say halo substitution. A complicated thing, but just say halogenation or substitution. That should be a suitable answer. Propane is another hydrocarbon form. Another hydrocarbon obtained in one of the fractions of fractional distillation. Write a balanced equation for the complete combustion of propane. Oh, all right. So when we burn a hydrocarbon, when we burn an alkane, what do we get?
Steam and carbon dioxide or carbon monoxide. But if it's complete combustion, you get carbon dioxide.
All right. So propane is C3, right? H. 33H.
5.
C3H, right? Propane.
Oh, sorry.
Burn it in oxygen. We can get our carbon dioxide and water. Okay. Of course, I trust you guys to balance it. I'm not balancing it.
What
No, I'm
about
just writing it.
state symbols?
Yeah, I'm putting the state symbols as well. I was saying I trust you guys to balance it. What's the state symbol of that water over there, please?
Gas.
Everybody know what is gas? Yes,
Because it's supposed to produce steam or something.
It's a lot of heat when you burn this, right? Propane, for those who cook, sometimes you can use propane to cook. And I'm sure you don't see liquid water in your stove when you cook. So if you see liquid water in your stove when you cook, then you're probably on the wrong planet. Propane. Propane is a gas or a liquid?
It's a gas.
Gas, okay.
Propane is a gas.
Yeah, it's a gas. So this is it. I trust you to balance. I'm not balancing it. Next question. Let's see what's going on quickly. Draw this dot and cross structure of covalent bonding in fluorine. Ten plus 2 is 8. Okay. Fluorine, how much? F2, okay, 2 Fs. What do we do, guys? Talk to me.
Sir, on the outer shell, like you have one thingy there, the unpaired.
All right, how much electrons do we have in all? In around each fluorine?
Sir, I think like probably like 7. Is it 7? I don't know.
7 on the valence.
All right. How much at year level? How much? Most atoms. How much electrons they need to be full and happy?
8.
8. Okay, remember 8. So around each of these fluorines, right? Right. What's electronic configuration of fluorine?
2 to 7.
2, 8. Fluorine. No, fluorine is not 2, 8, 7. Fluorine's first halogen. So fluorine has to be 2, 7. 2, 7 fluorine. Right. So this can take an hydrogen.
Because it's 9.
Huh?
Yes, I said right because it's 9.
All right, I'm not understanding, Richie.
As the fluorine number is 9, that's why.
Yeah. The atomic number of fluorine is 9, right? But what I'm saying is that in a valence shell, there is 7, and you can hold up to 8. Yeah. Let me make this one. Let me make this one. I want to make this one the cross one. Let me make this one the cross one. So on this side we have 1, 2, 3, 4, 5, 6. I will put the 7 on the front. So then it bonds with the next one. So this is how we do it. You make sure you have all the lone pairs around it. So each of them have they have the lone pairs here, the 3 pairs of lone pairs, the 3 lone pairs. You have the one in the middle here, you have the one from here, you have the one from here. These are dots. Don't mind my dots. These are dots, guys. These are dots. All right. And this is the answer. About the following. Are you hearing me?
Yes, sir.
To understand that.
You don't understand?
Also, I forgot. The way that's why I should that. But the count it wrong with so the way you never clear.
All right, not a problem, Richie. Not a problem. All right, as long as you understand. Isotope. What's an isotope? Talk to me quick. I'm not writing it. What's an isotope?
Sir, an isotope has like it has a different number of like neutrons or something.
That's Jade because she said something.
Sir, sir, I think it's the one
Richie,
where
Richie,
we have the same proton number.
Richie, give me a minute, Richie. Somebody was going before you. The female.
Sir,
Go ahead.
the isotopes are elements with the same atomic number, but different mass number, sir, and different number of neutrons.
Okay, so yeah, different mass number because they have different number of neutrons. Richie, go ahead now.
Sorry, sir, I didn't hear. That was the same thing I didn't say.
Same thing? All right, not a problem. All right, let us see. Which one of the following is down here? Which one of the following is the isotope of carbon? Which one of these are the isotopes? The first one, second, third one.
12 and 14.
12 and 14?
With the thing at the bottom, with the 6 at the bottom or something.
So this is an isotope?
1 and
Yes.
4. 1 and 4.
And the fourth one.
1 and 4.
With
So
the
why not
6?
this one?
Because that's not
because-
carbon.
I mean, it's
Because
not
that has
carbon.
7.
Oh,
Because it has
it's a
7.
Okay, I understand.
Sir, would that be nitrogen or something?
Well, the number suggests that it's an isotope of nitrogen, but the letter here is saying something else. So it's just something that I just can't understand. All right. 2 examples of radioisotopes and state one use of each. Very
Sir, iodine, and they use it to treat cancer. The isotope of iodine. And the carbon-14, which is used for carbon dating or something.
You see, like when it's a carbon-14, it's always nice if we can say iodine number, insert number here. Yeah, it's probably iodine 131. I'm not too sure, but it's nice if you can say the number, insert number here. I can say cobalt, whatever can be used for whatever. You can say uranium 200 and whatever is used for radioactive cells or whatever like that. All right, Richie, go ahead.
235.
235. I'm not really too sure. Richie?
So I have a question, sir. I heard you say to say iodine and then to say carbon 14. So I have to write out the number. Say I will just write it word like iodine, sir. I'll have to write it out. We lose mark if we don't write it.
I'm not really too sure if they go lose mark, right? But them ask for an example, right, of an isotope, radioisotope, I would have put the number in. So I know which radioisotope I'm talking about. You understand? Because there are different radioisotopes.
Oh, so you want to be sure? Oh, all right, thanks.
Yeah. I'm not sure if radioactivity was on that list, but I'm just going through the paper very quickly. Calcium, magnesium react with water, right? When calcium reacts with water, what happens, guys? Very quickly.
Sir, you get the hydroxide and hydrogen gas like you get the hydroxide of the metal and hydrogen gas.
So you get the hydroxide of the metal. So the hydroxide of calcium would be what?
Calcium
Calcium
hydroxide.
hydroxide, CaOH. And they get what else?
Sir, there's a 2 after the OH, CaOH2, open bracket, the brackets around it, and hydrogen gas.
Hydrogen gas. But you agree with that?
Yes, sir. She's correct.
Okay. You see all these things, right? You have to go check your book, check your notes. You have to just know how they react. All right, next one. Unknown elements, unknown element X is shown in table 3. Predict order of reactivity. So you have calcium, magnesium, and X. So order of reactivity here. Calcium, magnesium, X. What's our order of reactivity?
Sir, X would be the most reactive.
X would be the most reactive?
Yes.
Followed by?
Calcium, then magnesium.
Okay, no problem. Anybody know what X is? Trick question.
Strontium?
No,
So
it's
I'm
not
guessing,
strontium.
barium.
I know.
So I'm not sure.
It's barium.
Not sure. I'm not sure.
It's
Sir,
barium. It's
where
barium.
would strontium be? Would strontium be below it or something?
Strontium is below it, yes. It's barium, yes, Richie. Nitrogen 16 is used to aid plants growth. I'm just seeing that. Thank you for that, Robertson. I really don't want to butcher you guys' names. All right, in many Caribbean countries, hydrocarbons are used as a source of energy. State 2 natural sources of hydrocarbons.
Natural gas.
Mhm.
And the oil.
Okay, natural gas, oil, natural gases and petroleum. Okay, you can also have what do you call that? You have e-fuel, where you can have your compost, you can have your compost produce gases and stuff like that. That's also one. I'm not sure if you learned that here, but I think you learned that from like primary school. They never focus on it because there's assuming you don't remember. All right, so we have a 1 to 4. We're naming the fractions, right? So let's see who remember the fractions names. What's the name of the first fraction? Name any
Refinery
2
gas.
fraction. First fraction is refinery gas. Number 2, it don't have to be the same person, but remember you're naming 2 fractions. Refinery gas, what else?
I don't know.
Somebody else. Refinery gas. You're naming the fractions. So the first fraction of 1 to 4, you have diesel. Diesel, which fraction? What fraction is diesel? Is diesel a fraction? Number 2, diesel. Okay.
Sir, gasoline, or petroleum. Petrol.
Let me check something real quick. I think this should be coming on the paper. I'm double checking the list of things I sent. Activity, organic reaction, impact, non-metals, hydrocarbons. Yeah, it probably comes. Organic chemistry. This is on the organic chemistry. You guys need to know. You need to know the categories.
Sir, where would naphtha go?
Naphtha is probably the second group.
Gasoline.
Gasoline? I just said gasoline or something.
What about kerosene?
Kerosene art. Kerosene isn't the name of the group. Kerosene is one example of something that falls in the group. So you have refinery gas, you have petrol. So person said petrol, I guess we can get that. Kerosene. Oh, you're saying kerosene is a thing by itself.
Sir, I don't know. I'm just asking, where would it go?
Kerosene is 10 to 14. 20 to 40 is going to be
the
bitumen.
lubrication thing.
Bitumen. Lubrication is 18 to 30.
Okay, sir.
So you can put bitumen. Bitumen is what they might use on the road. Right, pitch tar. So it's just for you guys to catch up on that. All right. What's the name of this process? You're changing a long chain hydrocarbon alkane to an alkene and a alkane. What's this process called?
I think it's thermal cracking or something.
I know that's Jade because she said something. Methane. Methane falls into refinery gases.
So which is catalytic cracking? Which one is that?
Catalytic cracking is when you use a catalyst.
So sir, how do you tell the difference in the if you see it?
Catalytic cracking tend to have a lower temperature, right? And they would specify it is used in the presence of a catalyst. So it's like what they said, absence of a catalyst, is an X-cracking.
Okay, sir.
All right, so it's thermal cracking. State the conditions under which the process undergoes. What's the conditions for thermal cracking, guys?
I think it's 30 atmospheres of pressure and 700.
Yep, above 700. So above 700, you can have 30. The range is up to 70, so you can have it in the 30 range. That's all right. All right, so the hydrocarbon C4H10 is often obtained by the process obtained, illustrated here. State two uses of C4H10. C4H10 is what? What is this? The name of it?
Butane.
Butane. Yep. All right, that's Kimani, right?
Yes, sir.
All right. Yeah, butane is answer. Two uses of butane, please. Kimani, can go on. Go ahead. Repeat.
Yes, sir.
Two uses of butane. Somebody want to tell Kimani? Okay, go ahead. I think you're breaking up there. Send it. Come on, tell you what. Send it in the chat. Send it in the chat. You can see. Go not hearing. Well, I'm not hearing. I'm not sure if I was hearing. Somebody else want to add on the mic? What two use of butane? Naomi, go ahead.
Sir, it's used for fuels.
Fuels, okay. What else?
And well, that's all I know, sir.
Propellant in fuel, okay. What about cooking? You guys don't like to eat? You know, lunchtime coming up soon. Or you don't want lunchtime? You guys don't like to eat. It's in cigarettes, is it? Really? I never done that. There's something new. Why people smoke cigarettes?
Sir, I see them using it in blowtorch, the torch thing.
So it's used as a fuel in torches, yeah. Fuel in torches is used for cooking. I can't think of anything else it's used for. It's probably butane. It's a yes. Butane can be liquefied. So depending on butane. Butane can be used as a solvent as well, guys. Solvent. That's a little bit advanced. If you're struggling for things, you can put solvent. You can dissolve organic stuff. Remember, organic dissolve organic. Last part of the question. I think this is a 2.5 hour exam. Yeah, and we have been at this for 2.5 hours. We stopped with a lot of stuff. So that means that you guys are really comfortable at doing this. Last part of the paper, you have a minute. So let us consider the metals at aluminum, iron, lead. All right, consider those three metals. Can you explain the usefulness of one of these metals and the harmfulness of one of these metals? So
Sir,
let's go with usefulness first.
Iron is useful. Sir, it's useful to make hemoglobin in organisms that use hemoglobin as a protein to carry oxygen.
Okay, so we know that iron is important for that heme iron complex that is formed. You guys should know about complexes. Very nice. Any other useful
Lead can be used as an insulator for radioactive substances.
Let me look at the question again. Insulator, I know it can be an insulator. Okay. Usefulness, to living systems. Yeah, I guess.
Sir,
It's
it can
protecting us.
prevent.
It's protecting us. Yeah, I guess that's the answer. Yeah. Richie?
So could I use say aluminum? It can use like parts and them so that then could upset that for in like the making of parts in other.
All right. So when you talk about making up, I mean that's a use of aluminum. But how I internalize this question, I think they're asking how does this benefit like living organism? Like making a pot really.
Oh, sir, so I didn't understand that that they mean, sir.
Yeah, so they're saying metals are important to living systems and others can be harmful. So they're saying consider aluminum, lead, and iron and their compounds and explain the usefulness of one metal, right? And the harmfulness of one metal to living things, living systems. You gave some good answer. What about iron poisoning, guys? No, lead poisoning, guys.
Sir, it causes retarded children.
Yeah, everybody know about those lead toys they made back in the days. You know, you have lead poisoning from lead pipes. What how else can iron be dangerous? I mean, those are two things that come to my mind. You have lead poisoning, you have the iron being useful for that. You also have lead being useful in shielding, right? So I think those three answers should conclude everything. All right, how you feeling about this paper, guys?
Oh, sir.
Mm-hmm.
Sir, can't excessive iron cause harm to living?
I mean, excessive anything can cause harm, right? So I'm in agreement with that. Remember that iron. Something came up to you a while ago now. But I don't remember. Guys, if you catch up on your biology, for those who do biology, you know it can
damage the liver because it's stored there or something.
not really not too privy on that, but I'm saying just catch up on it. So I'm listening to you, and yeah, that makes sense to me. Remember, your liver processes a lot of stuff that happens in your body. So yeah. All right, so let's see. Anything else? What do you feel about that paper, guys? 2021. You did it in 2 hours and 2.5 hours, right? And it was a lot of questioning, a lot of explanation, a lot of everything, and that was the time of the paper. How are you feeling?
It wasn't bad.
Wasn't bad?
Too bad.
Wasn't too bad. It was 3 bad then. R4. All right. So we can start looking at paper. We can start looking at 2020 paper 2, right? And remember the break is at 1 o'clock. So break for an hour, come back. And resume. But let us start looking at this. I did say there was a
Sir, what
titration here.
about January 2021?
2021?
January.
It wasn't easy.
Sir.
All right, 2020. I'm checking my my database. I'm checking if I have January 2021, and I don't think I have it. Oh, I think I have it here. Here it is. You hate molds. All right, look, we're going to do some molds very soon here. I want to get the earlier ones out the way, right? We'll try and move a little bit fast on this one, guys. So things take forever to download. Try and move a little bit fast on this one so we can get somewhere. We can get more papers done. Want to go back to like probably 2017. I don't know if that's a stretch. All right, this is January, right? 2021. All right, lovely. Concentration of solution of, oh wait, am I sharing my screen? You're in the wrong paper. There we go. Are you seeing my screen? Are you seeing the 2021 paper? Am I talking to myself?
Yes, sir, we are seeing.
Okay, no problem. All right. 2.5 hours, of course. Let's try how much we can get done in half an hour. Concentration of a solution of sodium hydroxide in dm³ is determined by a method of thermometric titration with strong acid. The procedure used as follows. You transfer 25 cm³ of sodium hydroxide to a styrofoam cup. You don't know the concentration. You want to take the initial temperature of solution, then you're going to add 5 cm³ of sulfuric acid and stir the mixture. Of course, put the thermometer in there and stir it and measure the change, record the temperature. You're then going to repeat the procedure, adding 5 aqualots of sodium hydroxide until a total of 30 cm³ of sodium hydroxide is added. So you do it the first time, you add 5. You do 25 again, and you do it a second time, but this time you add 10. The third time you add 15. Fourth time you add 20.
Excuse me.
Mm-hmm.
You said sodium hydroxide, isn't H2SO4 sulfuric acid?
Sodium hydroxide, you're using sodium hydroxide for the, or you have sodium hydroxide first, you put that in the styrofoam cup. But if I was, you're supposed to add the sulfuric acid, yes. So if I said add sodium hydroxide, you added sulfuric acid. Apologies for that. If I said anything like that. All right. So these are temperature readings. So they added 5 cm³ of H2SO4. This temperature was 27.123456789. 27.12345. 27.5 for the first one. The second reading was like 33.4. And the last one was 28.9. Right? By the following?
Yes, sir.
All right, of course. So what they're saying is using temperature readings here, complete the tables by recording the temperatures for that. So you basically just go read off these thermometers. Like just give it an answer. Oh, that's wonderful. Oh my lord. Then you're going to plot the graph. Right? Let me see. We all know to plot the graph. Let me just open up Excel real quick. See if I can share my Excel file. Excel. Okay. I'm gonna plot the graph real quick. So we have 0, 5, 5 equal above plus 5. Okay. $30. Okay. Then we have 25. I think next one was 27.12345. 27.5. They have 30.5. They have 33.4. 1, 2, 3, 4. They have Oh my lord. 32. Oh, sorry, this is 30. 20 is 32.5. Then you have 28.9. And last one is 28.9. Last one is almost 26. All right, so they say we're supposed to plot this against each other. I see that you guys know how to plot graphs or whatever, as per usual. We're plotting temperature against volume. So temperature is temperature, volume. Yep. You said draw two best fit line through the point, to the point, and where the temperature is increasing and the temperature decreasing. So of course we'll draw two lines, one going this way, one going this way, and the peak line, the end point of the reaction. Of course, you wouldn't have learned this. Don't know why this is on paper 2. Paper 2. January. Was it be a paper 3 then? All right. Anyway, you probably wouldn't get a question like this. Unless I finish syllabus. Were you guys exposed to a graph looking like this?
No.
No? Okay. You probably wouldn't get this question then. Okay, you're going to draw two lines there. You're going to see the peak point where the lines, you go draw two straight lines here.
Sure, for the thermometric titration, that graph.
Repeat?
So the graph you're referring to is the thermometric titration graph? That's that graph?
It is a thermometric here.
Sir, I've seen it before in another lab book, but I didn't do the lab.
Yeah, I don't think they do it for the June people. All right, what's a weak acid and what's a strong acid? This might come. Weak versus strong.
Sir, a strong acid ionizes completely in solution and a weak acid does not.
Edward, you have the same answer?
Yeah.
Okay, no problem. Of course, you plot the graph here. Balance equation between NaOH and H2SO4. What do you form?
Sodium sulfate.
And
water.
Water. Okay, no problem. All right. Calculate the moles of H2SO4 using reaction. Lovely. Who said them do like moles? Edwards. Yes. This is fun. All right. Calculate the number of moles of H2SO4 used in the reaction. Somebody said yes. Oh my lord, this is fun. H2SO4. Oh, so we're going to need to know the endpoints. All right. So let me just give you an endpoint real quick. Let me just extrapolate on my graph and give you an endpoint. Let's say the endpoint, when you extrapolate, the endpoint is around, this looks like, let's say 35 cm cube, right? 35 cm. Let's extrapolate and we'll say we use 35. Sorry, let's say we used, can I write instead? Yeah. So we used 35 cm cubed of sulfuric acid. Right? Is that much cm cubed of it? And it should be noted that we combine this with 25 cm cubed of NaOH. Nastasia, talk to me. What's when you combine them together? Remind me of the chemical equation that's going to happen now, please.
The chemical equation. H2SO4 plus NaOH is NaSO4 Na2SO4 plus H2O.
Plus H2O. Okay. Is it balanced, Edward?
No, it's not.
Talk to me.
I think you need to put that 2 beside the NaOH, beside the Na and the NaOH.
This right here?
Yeah.
Okay. Is it balanced now? Is it balanced now?
No, I don't think so, because I think that 2 needs to go beside the water.
Somebody want to help? All right, 2 beside water, or is it balanced now?
Yes, sir.
Yeah.
Balanced? Okay. All right. What's the mole ratio? How much sulfuric acid goes towards each NaOH? What's the mole ratio?
1 to 2.
1 to 2. All right. You see that as well, Edwards? Edwards?
Yes, yeah.
You see that, right?
Yes, I can see that.
No, all right. Do you understand that? Let's get technical. The mole ratio between sulfuric acid and NaOH is 1 to 2.
Yes, I understand.
Okay, good. All right. So that means if I have 1 mole of H2SO4, how much moles of NaOH do I need to react with that? Yeah, it's 2, right?
Yeah.
So if I have 4 moles of H2SO4, how much moles of NaOH I need?
8.
Okay, so you understand moles. What's the problem? Anyways, let me see what else is going on here. So 25 cm cubed, which concentration did we know? Let me go back to the question and see which concentration we know. We know the concentration of the acid, right? Acid is 0.1 mole, right? What does 0.1 molarity mean to you?
I think it means that there's 0.1 moles in 1,000 cm cube of solution.
Okay, so you understand moles. What's the problem? All right, so 0.01 moles of this, right? 0.01 moles of the H2SO4. I'm writing it under it because it's of that one, right? Do you know the formula for molarity?
Not really. I don't really use formulas. Really.
You use formulas, okay. How would you calculate how much moles of H2SO4, if this is a concentration, how much moles exist in 25 cm cubed? Talk us through it. Don't just give me an answer. Talk me through it, so everybody can hear what's going on.
Sir, volume times concentration.
The volume times who tell me that? Is Edward telling me that?
No.
Who is this? Who is this?
Sir, Shantoya.
Shantoya. So you know, all right, I appreciate that, right, Shantoya? You use a formula, but what's her name? Edward is saying that she knows a formula, right? So I want her to talk us through it, right? So, and she said she don't really understand. But yeah, you're right. Volume times concentration. Edward, you here?
Yes, I'm here.
Talk me through how you find how much moles in 25 cm cube, if this is concentration.
I'm not too sure what to do after this point.
All right, you say you know his formula, right? So let me try to break down the formula for you, right? Okay, you will come back down to the same formula. You might afraid of the formula, but for your sanity, it's best you know the formula. But let me break it down. What does this mean? 0.01 molarity means that we have 0.01 moles in 1,000. But I agree with that.
Yes.
Is Edwards alone agree with that? Everybody else agree with that?
Yes, sir, I agree.
Okay. So if this goes into 1,000 cm cubed, right? What you're trying to find is how much moles X goes in how much? 25. The answer, that might be the answer, Kayla. I haven't worked out yet, but what I'm doing, I'm trying to walk Edwards to it. Edwards says she don't understand most.
No, sir, I think she's saying it's 0.1 moles of solution, or the molarity is 0.10.
0.1. Okay, let me double check real quick. 0.1. Yeah, 0.1. Thanks for that. Right here. 0.1. Thank you for that. Let me put erase 0 right here. So 0.1, 0.10.
Oh yes,
Right?
that's what I usually do. I had forgotten, but that's what I usually do.
Edwards, if I slap you, say Jesus and 15 disciples. All right, let's see if I can finish working this out and get the answer.
Sure. Why won't you use the 35 centimeter cube instead
Why
of
would you
25?
not? Oh, yeah, look at me writing foolishness. So you're right. Because we're supposed to use 35 because it's for the sulfuric acid. Me writing foolishness. Because I was here failing to believe that this girl don't know how to do that. Kimani, go ahead.
Excuse me, sir.
Mm-hmm.
Also, according to what you have on the screen, if there is 0.1 moles of sulfuric acid in 1,000 cubic centimeters, then there will be X moles in 35 cubic centimeters. So you just have to cross multiply to find your answer.
Yeah, that's how we do it. We're doing it this way because you use the formula, Kimani.
No, sir, this is how I do it.
That's what you do it? Yeah. We do it this way because Edward says she never know how to do it. And says she don't use formula. How do we get 35? Because them tell us. Well, I extrapolate, so I'm telling you what it is. I suppose you're supposed to get from the graph, Kayla, from this graph, but the graph look kind of weird. It's a thermometric graph, right? Let me share the graph again. Kimani, go ahead. This is how the graph look, Kayla. So I just extrapolate to that. The top part is 35, right? And I just give it a 35 as the answer. Kimani, your hand raised up.
Oh, sir, that was an accident.
Okay, no problem.
Yes, sir, I had a question about the graph.
Mm-hmm.
Well, the graph never really took up, like, it never took up most, like, it started at 25. Isn't it supposed to take up like 75% of the graph?
All right. This graph here, I just plotted it on Excel, right? More than likely, you're not going to get this graph on your exam, right? But I was doing the question for the sake of explaining moles. Understand?
Oh, okay.
Yeah. Earphones are dying. Let me check my next earphones. Okay. All right, can you still hear me?
Yes.
All right, no problem. I think my writing came off. So I'm going to have to do all that over again. But basically what's going to happen is that, oh my Lord, what's going on here? What's going to happen is that we're going to end up with 0.1 goes to 1,000, right? And we're trying to find how much goes to 35 cm cube, right? You're trying to find how much goes to 35 cm cube. So you just cross multiply whatever answer you get here. 0.1 times 35 is 3.5. So 3.5 is equal to 1,000x. Tristan, oh wait, Tristan is trying to come in. Okay. Equal to 1,000x. I just solve for x. Right.
0.0025 moles of sulfuric acid.
0.0035. Repeat.
0.0035 moles, or 2 times 10 to the third power. 2.5 times 10 to the
third
moles of sulfuric acid.
Okay, no problem. Thanks. Yeah, so that's that. All right. I didn't do it over again because I don't know my writing disappeared. But that's that for this one. All right, so for the graph, wouldn't 2 lines be best fit, or the case as an endpoint? They join 2 straight lines. So the graph, the points that are going up on one side, the points that are ascending on one side, you draw a straight line through that. And the points that are descending on the next side, you draw a straight line through that. And wherever the 2 lines them intersect, that would be your endpoint. How did you get the 35? I did the extrapolate. I did that, whatever I described to you, I did it myself and I gave it 35. That's what I did. All right, so since you guys have been quite engaging, I'm gonna let you off a few minutes early. We'll come back at 2 o'clock, right? We'll come back at 2 o'clock. Resume 2 o'clock. We're going to work out the concentration for NaOH, work out this most question. And I don't think I'm going to go much further in this paper. Now let me just look through and tell you from now. Calculate this in grams. Yeah, I'm going to do this question. I'm doing this question as well because it's energetics, ectothermic or endothermic, and precaution. Yeah, I might go through a few more questions in this paper, but remember we're trying to get down to. Yeah, I might do this as well. Ethanol. We'll do a few more questions in this paper. So we'll come back at 2 o'clock, guys, and we'll resume. What's going on with this computer? Resume here. Resume here. Finding the moles of NaOH. All right. So have a good lunch, guys. If there are any questions, I'm here open to answer or talk with you. You don't have to leave. You can just go ahead, have your lunch. But I'll do a roll call at 2 o'clock to make sure everybody's here. So if there is any question, raise your hand from now. Let me know.
So I have a question, sir. After this meeting and today, after this marathon and today, group still be there, sir. Like group stay there, so we can still access and then I close group.
You're breaking up, but what I take from that, you're saying that if you can ask questions in the chemistry group?
After this has ended.
Oh, definitely. Feel free to ask me questions in the chemistry group. You can. I'm not one to give you questions, prompt you with questions like that, because I am not really too sure where you are academically, right? I don't know if you spot that. That would be something on the end of a teacher. Going into the profession of teaching, that's what I intend to do with my students. But you, if it's, I want for you to take the initiative to just, if you write questions and you want to run it by somebody, for example, if a Peter can't run it by a teacher, you can always run it by me, Not a problem. I'll see how fast I can answer in the group. Appreciate how professional group has been. You guys don't really send anything stupid in the group. But yeah, feel free to ask questions or anything like that. Just keep it chemistry related.
Respect, sir.
Not a problem. All right. Was that Anthony?
Yes, sir. Want to test for me to after the meeting?
You want to speak to me after the meeting?
Yes, sir.
That's in after we finish at 5 o'clock. We're finishing everything at 5 o'clock. So you want to speak with me at 5 o'clock? Or you want to speak to me now? You want to speak to me now?
Yes, sir. No. Yes, sir. No.
You want to speak to me on this platform?
Yes, sir. Yeah, that's okay.
All right, give me a minute. Let me send a voice note. All right, go ahead, Anthony.
All right, so yes, I'm from Homologous High School, and I'm in fourth form, but I always want to do computer engineering or repairing, but my course is business studies. Then later on, when I realized that I couldn't do the subject that I needed for computer repairing, it was too late to change my course. So I started a chance to try to catch up on chemistry and physics. So I don't really know anything about these subjects like chemistry, physics, and the others. So I'm wondering how could I catch up in the meantime before or until this time for me to do 60, which is next year.
All right, so you're asking me for advice as to what you can do to catch up with chemistry and physics?
Yes, sir. Like the topics that I would need to catch up on.
Okay, recording is in progress. Admit people. Okay, Last time we were here, we answered how much moles of H2SO4 was there, all right? Anyone remember how much moles we worked out to be?
0.0035.
3.5 times 10 to the third power, or negative third power.
All right, 3.5. Thank you for that. First person, I identify that voice. Well, who went first?
Shakira.
Shakira, all right. And the person that went after was Jabari, right?
Kimani.
Kimani, all right, no problem. So 3.5 times 10 to the negative 3, right? And this is for H2SO4. Now, it's very important for us to use the moles of what we know to find those of what we don't know. We have to use the mole ratio to find how much moles of KMnO4, of NaOH. The reason being is if we use something else, then we're not going to get the right answer, right? So if you're saying 25 cm, how much moles in 25 cm cube? We have to use the moles of sulfuric acid to determine it. All right, so somebody tell me how they would answer this question. Instead of me answering, how will you answer this question? Raise your hand and go ahead. Raise your hand analogy and go ahead. Gabriel, go ahead.
You'd have to use the mole ratio.
Talk me through that. How you get to the mole ratio?
Alright, so if you go back to the reaction and wait, can you go back to the reaction, please?
I can type it up right here, so real quick. Okay. Yeah, when you use the reaction, what happens?
So if there's like a number in front of it, well, if there's no number in front of it, then automatically it's 1, and you'd use the same amount of moles. But if there is a number in front of the NaOH, then you multiply the amount of moles in the H2SO4 by the number in front.
Is that always true, though?
Well, I'd say yes.
Yeah. Then what can I say? What if trying to move something like, all right, let me hear from somebody else first. Shakira.
Yes, sir. So 1 mole of sulfuric acid reacts with 2 mole of NaOH. So that means the amount of NaOH that reacts is 2 times the amount of moles that react. So we got 3.5 times 10 to the third power negative. So we would multiply that by 2 to find the amount of NaOH that reacts.
All right. You multiply it by 2 because it's a 1-to-2 ratio, right? So Gabriel, so the reason why I ask is that what if a 2 was in front of this acid right here? If a 2 was here, right here, right? Could you do the same? What would you do if a 2 was right there? So what would you do?
Oh, you'd need to use half.
You'd need to divide. Yeah, so it's not always that you multiply automatically based on the number. You'd have to determine, right? So it's not because there's a 2 there, not any random 2 would make you have to multiply. You have to determine what the 2 is saying, right? Because it's saying 1 to 2.
Oh, okay.
Yeah.
Wait, hold on. Just one question though. If let's say there was a 3 for the H2SO4, then a 2 for the NaOH.
Wait, let me get this. So if there's a 3 for one and there's a 2 for next one.
Is there like a 2 over 3?
All right. Let me get an equation for you. Right? Let me get the equation for you and add with somebody. I just erased that by accident. Let me see if I can undo that real quick. Let's see if I can get the equation for you. All right. So you're saying there's a 2 to 3. Kimani, you have a question?
No, sir, I was finishing the current question, but when we finish with this.
All right, not a problem. Let's say 2 to 3. So let's say iron 2 plus let's say iron 2 plus is iron sulfate. SO4. All right. I don't know if you just want to draw. Protein is acting weird again. Iron sulfate plus let's say, so let me think about something that has 3. Iron has 3, no. Aluminum. Two to 3. Oh, you know what I can do? Why am I overthinking it? I just create salt and I use acid and base reaction. I'll think about the redox reaction. Sorry. All right. Give me a, all right. Give me a, somebody give me a dibasic acid. You guys know what a dibasic acid is?
You could use sulfuric acid.
All right, sulfuric acid. Let's use sulfuric acid. Give me a tribasic. All right. Give me a tribasic acid and a dibasic base. Tribasic acid.
Phosphoric acid.
Phosphoric acid. So let's just use H3PO4. And let's use, give me a dibasic thing, please. Dibasic acid. Base, sorry, dibasic base.
Magnesium hydroxide.
Dibasic base, magnesium hydroxide. Okay. This is Kimani, right?
No, Gabriel.
Gabriel, yeah. Gabriel said you wanted some help with this thing. All right. So balance this for me, Gabriel. I know there's a 2 and a 3 here somewhere going on. This supposed to have water. What do you form at the end? Water and what?
Magnesium phosphate.
Magnesium phosphate. Mg
2 3. Mg3.
I think Mg3. Yeah, I go delete that. I go delete this. I go delete it too.
Okay.
Yeah, balance it for me. Balance it. I wait. All right, correcting this. Balance this for me.
All right.
This balance?
12. 6. There needs to be a 6 in front of the H2O.
That's the only thing that needs to change?
Yeah, I think so, because there's 12. There are 12 hydrogens.
Okay, no problem. All right. So what Gabriel is saying, Gabriel, repeat the question again. If there's Gabriel, sorry. What's your last name? Davey. Okay, Davey. Repeat the question.
So like in the event that there's a mole ratio of 2 to 3 or 3 to 2, what do you do?
All right. Everybody understand the question from Davey?
Yeah.
All right. So if there's a mole ratio of 2 to 3, right? That means, let me get my pen right here. So that means 2 of this. Let me make it simple. 2 of this, 2 phosphate. Let's call this phosphate. 2 of this maps on to 3 of this. So 2 of that. You need 2 of that to make 3 of this. Let's make this a square. All right. So 2 of this. H3PO4 maps onto 3 of the magnesium hydroxide. Right? And all you just scale accordingly from there. So long story short, I don't know if you said it, But yeah, there will be a fraction thing going on. So you divide this by 2. You divide this by 2. And you end up with 1 going on to like 3/2 or something like that. I don't know if you asked that question, but yeah, if they ask that, then yeah, that's the answer.
Okay.
Okay. My
Also,
coming.
it depends on the thing on the right.
It depends on both of them.
Oh, both of them.
Because what my thing on the right?
Like the compound, I guess. Like I just see it like an equation.
Which compound are you talking about? Which compound on the right?
The magnesium.
Remember, you can always put magnesium in front of it.
Oh.
Yeah, the order in which you write the equation doesn't matter. It's for you to identify the ratio.
Oh, okay.
Yeah?
Okay, sir.
Yeah. Everybody's clear with what just happened? If you're not clear, raise your hand. Baby, your hand is up, by the way. If you're not clear, raise your hand. Okay, so we all clear. All clear. Trying to erase this very quickly. All right, so we have our equation here set, and our mole ratio is I erase the mole ratio. Our mole ratio is supposed to be 1 to 2. It's supposed to be 2 over here. So there's a 1 to 2 mole ratio. So that means we just multiply this by 2, as just said earlier. Multiply this by 2 and we get the answer, right? When we multiply it by 2, what answer do we get?
7 times 10 to the negative 3.
7 times 10 to the negative?
Moles of sodium hydroxide.
7.10?
I said 7 times 10 to the negative 3 moles of sodium.
It's negative 3. Okay, yeah, so this answer. Okay. Okay, guys. Let's move a little bit faster. Find the concentration. Somebody answer this quickly. Let's see if we can get this. Find the concentration.
If there are 7 moles or 7 times 10 to the negative 3 moles of sodium hydroxide in 25 cubic centimeters of solution, then there will be X moles in 1000 cubic centimeters, and that will be concentration in mole per dm cube.
What's the answer? Work it out and tell me what's the answer. What's the answer, guys?
Point 0.28 mole per dm cube, or mole to the negative 3.
Repeat that. I didn't get that.
0.28.
0.28. All right. There we go. All right. Yeah. All right. So let's keep going. Let's keep going. Let's do this one as well. Calculate the concentration of it in grams per dm cube. So the molarity, the moles per dm cube was 0.28. So the molarity was 0.28. So find the grams per dm cube. Nobody? Any volunteers? Stacy? All right. Smith?
Sir, the answer is 11.2 grams per dm cube.
How did you get that answer?
Right, so 1 mole would be equal to 40 grams, and 0.28 moles would be equal to X.
No, wait. This is 0.28 in 1,000. Does it still work? Let me write it out for you. One mole is equal to how much? 40 grams?
Yeah, because the molar mass.
Okay. And you're saying?
And since we have the molar volume, so 0.28 moles.
0.28 moles. Is this 0.28 moles though? Oh, all right. 0.28 moles. Okay. Molar volume. Uh-huh.
Yeah, would be equal to X.
Equal to X.
Yeah, then cross multiply.
Okay, what answer you get at the end?
11.2 grams per dm cube.
11.2. So I have a question. What if they didn't make you? No, I think this works in all situations. Is there any other any other way? Everybody understand this question? Everybody understand the answer?
Yes, sir.
Is there anybody who don't understand? If you don't understand, raise your hand. Okay, good. All right, moving on. All right, so tell me, guys, you remember, is the exothermic or endothermic reaction? You mix acid and you meet acid and base together. Is it exothermic or endothermic reaction?
Exothermic.
All right, so for those who say exothermic, lift up your hand. And for those who say endothermic, don't say anything. For exothermic, lift up your hand. All right, exothermic, lift up your hand. I think it's endothermic. See? I will defend my point. Let me pick somebody from exothermic group. Travis, why is it exothermic?
Sir, I think heat was produced.
It produced heat. So that's a trait of. So wait, what's the difference between exothermic and endothermic?
So exothermic produced heat, and endo absorbs heat.
Absorbs heat. All right, no problem, no problem. All right, fair answer, fair answer. One precaution that could be taken during the experiment. Anybody? You mixed sulfuric acid with sodium hydroxide. Name one precaution. Anything could have been taken.
So you could set up the area of the experiment in a way that minimalizes the heat loss to the environment.
Okay, how would you do that? What do you mean? You have to be specific, you know. I know you.
You could work in an enclosed space with like no blowing air or something like that, or no breeze in the vicinity.
Okay, that's one thing. Safety precaution. So safety goggles, safety precaution. So what you shared with me, was that Kimani or Gabriel? Gabriel? Wait, Kimani?
Kimani.
Yeah, all right. What you shared with me wasn't really a safety thing, you know. It was like a procedural, methodological precaution. You know, if you know what I mean. It's not really safety like that. You could have wear gloves, you could have wear goggles. Those are things to do with your safety. Yeah. You could have added you could have a lot of things for safety reasons. Using a colorimeter, that's not for your safety. In fact, the styrofoam is a makeshift colorimeter. So think along the lines of safety, guys. Safety in the lab, right? That's how you'd answer this question. All right. Of course, we know this. I think this should come on an exam. RNS are isotopes of carbon, right? R is a black opaque solid. It's described as flaky, a melting point of 32.25. S is a reflective colorless solid with a melting point of 38.23. What's the allotrope? I said isotope. I know I said isotope. What's the allotrope, guys? What's the allotrope?
The allotropes are different forms of the same element existing in the same physical state.
Compounds from the same element but have different physical states? That's what you said, right?
I said existing in the same physical state.
Same physical state?
There are elements with same chemical. Wait, they're the same element but different physical compositions, meaning different structures, chemical structures.
Okay. I acknowledge that answer. I don't really understand that first definition I was given. I don't really understand. I don't really understand. First, I want to repeat yourself. I'm listening if you want to go again. I did understand your definition. Was it right? Right, you're the person who went, right? Hello? Okay. You guys are silent for nowhere, man. So yeah, it's basically different structural forms of the same element. Different structural forms of the same element. Can you have a solid and a liquid? No, you can't have a solid and a liquid. That means you can probably put in the same physical state as well. All right. Anybody, what is R and S?
R is graphite and S is diamond.
R is graphite, S is diamond. All right. I think Edwards had her hand up. Is Edwards or is the next person? Yeah, Edwards. So Edwards, is R, state whether R is ionic, simple covalent, or giant covalent.
I'm not quite sure, but is it simple covalent?
All right. Anybody want to help out Edwards here?
Covalent.
Giant covalent.
Giant covalent. All right. What's the difference, guys? What's ionic? Let's start from ionic. What's ionic?
A metal and a non-metal that's bonded together.
Okay, so we know what ionic is, right? Now, what is the difference between giant covalent and simple covalent? Anybody?
Is it that the bonds in the giant covalent are stronger and harder to pull apart than the simple?
Not necessarily. Sometimes, but it's the same covalent bond.
Wait, is it that for giant covalent, it has the same element and a simple covalent have different elements bonding?
I have a question. That's Kimani, right?
No, Gabriel.
Gabriel. All right, Davey, tell me something. Is ice a giant covalent or simple covalent?
I think it's simple.
Does ice have different compounds in it? You said compounds. Where do you use compounds?
Oh no, different elements.
All right. So my next question is iodine a simple covalent or a giant covalent?
Probably giant covalent.
Why would iodine be giant covalent?
Because it's bonding with itself.
All right. So iodine is not giant covalent, right? A giant covalent is something that how do I put this? A giant covalent has a a large repeating structure. So it's like something that it repeats continuously, right? And it's much larger than the simple molecular, the simple covalent. The giant molecular covalents, I think you'd also find them with more they tend to form these things called macromolecules. You know what macromolecules are?
Yes, sir.
Yeah. So them tend to form like these things that the macromolecules. Right. So you think about things like diamond, you think about things like graphite, think about things like silicon dioxide, things like that.
Oh, so it's like multiple bonds forming even larger bonds.
Yeah.
Oh, okay. All right.
And in addition to that, giant covalent crystals and stuff like that, they tend to compose of only non-metal atoms, basically. Whereas simple covalent can have like sprinkles of metal atoms and stuff like that. So like you can have the hydrogen from the in the ice. What actually happens in ice? You have let's put it this way. Anybody know how ice freeze? Anybody know how ice freeze? Anybody who don't know how ice freeze?
Hydrogen bonds get stronger.
Yeah, so you know about hydrogen bonds, that's good. So in simple molecular, right? In simple molecular, so next defining feature, in simple molecular, you have these strong covalent bonds, right? You with me? Yeah. Yeah, so you have these very strong covalent bonds here. But what happens to make the lattice, which happens not to be a macro lattice, macromolecule, is you have these weak interaction. So the hydrogen is going to be weakly attracted to this oxygen over here. And then this oxygen is going to be weakly attracted to this hydrogen. And it goes on and on like that, right across. Right? And these hydrogen bonds are weak. Yeah. So they can be broken easily. So even though they stay into this, they can form these lattices. Like they're not necessarily the most stable of lattices. You get me? You following Davey?
Yes, sir.
All right, good. So that's the difference between giant and covalent. A giant covalent, it took some talking to get to that point. Giant covalent wouldn't have these bonds. Giant covalent would be strong throughout, right? And then the simple covalent would have these weak interactions between either hydrogen bonding. You guys know van der Waals bonding? You know van der Waals?
Yes, sir.
Yeah. Van der Waals, yeah. Van der Waals. For those who don't know, van der Waals is spelled Van der Waals, but it's spelled weird. Van der Waals would happen between iodine bonds, the iodine molecules, so they can easily sublime and stuff. So this is van der Waals. Yeah. So yeah, that's the difference. So R is graphite, and graphite has strong intermolecular force. It has van der Waals, yeah, but it doesn't result in the core structure being destroyed. Because remember, the core structure are those. How does graphite look? I'm not giving it away. What's the core structure of graphite?
Hexagon.
Hexagon, good. I didn't get the name of person who was going, but I realized the background was loud. But yeah, it's hexagonal. You sketch the structure of R using solid lines and show strong bonds and dotted lines to show weak bonds. All right. So you said it was hexagonal, right? Everybody know how graphite looks?
Yes, sir.
What happens when graphite is being formed? What happens to the carbon bonding? How much other carbons are bonded to?
3.
So one carbon here is bonded to 3. 1, 2, 3. The carbon over here. So this carbon is bonded to 3. So this carbon is on to 1, 2, 3. I go with 3 go up here. So right. I'm just going to do the what do you call that? I'm just going to do the carbon writing for the first ring because it gets a little bit complicated. But when you go in the exam, draw all the carbons, please. Please draw all carbons. So this is one ring, right? And this is connected to something else, and it goes up here, over, down, here. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4. It goes all the way over, guys. Yeah, this is one layer. They go over next layer under it. You guys following?
Yes.
Yes, sir.
All right, no problem. Up, across, over, down, here, 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 here. And they, of course, these are the strong forces and they have weak forces between the layers. So these are dotted lines between the layers. This is the weak force here. All right, guys. So this is how the bond would look. This is how the graphite would look. Right? All right. Let's see if we can move on to the next question. Everybody got that? I'm going to clear the screen.
Yes, sir.
All right, no problem. All right. Explain why R you said is graphite. Why does graphite conduct electricity but S doesn't? Why? Anybody?
The weak bonds between the layers allow for a free flow of electrons.
Okay, that's Dave, right? Kimani. Okay. All right, I hear you. Anybody else?
Same thing.
Same thing. So both tell that's the wrong answer. What do you want to change them, man?
Is it because there's mobile electrons present in graphite to conduct electricity?
Yeah, the mobile electrons are there now, but where are these mobile? Are they? Is it facilitated because of the weak bonds?
So because each carbon is bonded with it.
Yeah, all right, yeah. I think I draw the wrong thing here because each carbon is bonded to 3 other carbons. Right, guys? Let me draw the covalent thing for you guys can see. Right? Let me draw the covalent thing for you. So I have a carbon here, right, guys? And I have 3 other carbons around it. 1, 2, 3. Who's that? Shayon, can you please? Thank you, Shayon. I hope I didn't destroy your first name because I can't pronounce your last name either. Sorry. All right, so these are carbons. Just assume that these are perfect electrons. I'm trying my best to try to get them quickly in. Right, so each carbon is surrounded by a valence shell of 2, 4, 6, select 2 plus 2 is 4 2 plus 4 is 6 electrons here. They're surrounded by 4 electrons in the valence shell. I'm trying to say. I think I draw this wrong. All right, let me get my eraser real quick. All right, let me just erase this real quick. Erase this. Erase this. All right, so you understand what's going on here? You guys?
Yes, sir.
All right, so yeah, basically what's going on here is each carbon, so this is one carbon, but you can imagine that each of these other carbons have three other carbons to surround it. And this is what happened at the individual carbon level, right? So this singular carbon has how much things it have around it, how much electrons have around it for itself. Guys? 5? What structure? That's the structure of graphite. No, that's not the structure. I'm answering next question.
4, sir.
4. It has 4 electrons around it. So the 4 here. I'm just drawing it again. Had them in X's, so I decided to put them in circle. Now 4 electrons. Every carbon has 4 electrons around it, right? And look what happened when it decides to have. If it decides to have 4, right, in an ideal world, how much things can go around carbon in an ideal world? Ideal world, how much things carbon want? Guys?
Repeat that, sir.
4. How much elements, how much things carbon want to be bonded with in an ideal world? 4, right? Yeah, 4. So look what happens in an ideal world. Right? Look what happens. You have the 4 carbons around, the 4 electrons around this carbon, right? And how much, remember octet rule? Octet rule say that atoms are happiest when they have 8 electrons around themselves. What happens in an ideal world? These 4 electrons, these 4 atoms around it contribute these electrons to it. You see? It share the electron with it. When it starts sharing, it's going to have 4, right? And it don't share 2. Sorry, I draw it wrong thing. It don't share 2. It share 1. 1 it share. Okay, you need to share with its other neighbor. So it share, each of these things share 1 with it. Yeah, there we go. Each of them share 1, right? I'm going to draw it in properly for you. Each of these carbons share 1 electron. See there? 1 electron. And each of them share 1. This central carbon is happy now, right? Because it have 4 people around it sharing 1 electron with it. And this make it happy with the octet rule. You see that? Came out here, your background kind of loud. So it's happy with octet rule. So what happens, and this what happened in graphite. This what happened in diamond, right? You know, each of them is surrounded by 4 other carbons. So there's nothing going on here, right? So in graphite now, you said to me that each carbon is surrounded by 3. So if I take my eraser and erase this carbon over here, right? What has changed? Somebody tell me what has changed.
Sir, the central carbon will only get 3 electrons.
So it has 3 pairs and what is left?
1 mobile electron.
1 mobile electron here. Thank you, right. There's a more. Yes. This is why it's able to conduct electricity. I can imagine millions and millions of these carbons stretched across, and all of them have this free electron here that's not bonded. They can move. And you told me that electricity happens because of mobile electrons. So this is where the electrons come from in the graphite. All right, everybody understand? Everybody understand?
Yes, sir. Yes, sir.
All right, no problem. All right, let's say that another solid T is white in color. And it has a melting point of 809 Celsius, right? It conducts electricity when molten, but not in its solid state. Them asking you what kind of bonding is present in T? What kind of bonding?
Ionic.
Ionic bonding. Yes, 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 yes. That's the answer. And you can give me a guess. State appearance that it will have. How you think it would look?
Crystalline.
One person. Let me hear from Travis. Travis, go ahead. Thank you, Manny. Travis first. Travis.
Crystals.
You have crystals. All right. Kimani.
Sir, a white crystal like solid.
All right. So we're all saying that it will be crystalline. Because it's ionic, right? But no, ionic structures have these repeating crystalline lattice that lead to its particular thing, right? For those who wondering what I'm talking about, you can think about like table salt. Look at table salt, they have a cubic crystalline structure. Guys, chemistry is nice. There is not only cubic crystalline structure you have other things. You have orthorhombic, you have all kind of things. All kind of things. Let's not go into that. Insert add here. All right. Solids, liquid, and gases are easily converted from one state to another. All right, I don't think I need to go over this, right, guys? Compare particles in solid and liquids. Arrangement of particles. We know to this, right?
Yeah.
Yes, sir.
Yeah, this is third form stuff, guys. When iodine is heated, purple gases evolve. What process is this? Solid iodine is heated, purple gases evolve. What do you know? This is called S word. Let's say quick.
Sublimation.
Yes. Sublimation. Give an X component undergo sublimation.
Dry ice.
Dry ice. Thank you. So dry ice is what I'm use. If people who like live in country, the ice man come around. That is dry ice is what the ice cream man used to keep him ice cream full. All right. So, okay. We already defined what isomerism is. Structural isomerism. So I used the wrong word before. I think I said Alex word. It's not structural isomerism I said before. I was thinking that's a bit complicated. All right. So we define isomerism already. Somebody help me draw this, please. 2-methyl butane. Anybody?
First, you draw a straight chain with 4 carbons.
Okay, I was going to ask you what kind of chain you want to know. Straight chain. Why it have to be straight?
Sir, because the branch is going to be on the second carbon. You can't have a branch. So it have to be a straight chain.
Okay. Naphthalene, yes, naphthalene is also one. Yeah, you guys know how naphthalene looks? Just fun fact. The structure of naphthalene. This is how naphthalene looks structurally. Sorry. This is not answer for here. I'm just drawing naphthalene. This is how naphthalene looks, guys. For those who curiosity. I forgot about naphthalene. Okay. This is how naphthalene looks. I think there's one here and then there too. This is how naphthalene looks. The whole chemistry what deal with naphthalene and naphthalene-like compounds. But yep, back to the structure. You draw a straight chain. Talk to me. Who's talking? Talk to me.
Right.
Right, right. Yes, you're right.
Yes, sir.
Excuse my pun. Go ahead, right.
You're going to put a methyl group on the second carbon.
What's the methyl group?
A group consisting of 1 carbon and 3 hydrogens.
All right, guys. So somebody help me here. Not right. Somebody help me. How I find carbon number 2? Which one is carbon number 2? Which side do I count from? Does it matter?
It does not matter.
No matter. All right,
Right.
good. So let me count from this side. Yeah. Let me go from this side.
The side
Yeah.
with the lower number, with the lower.
The side with lower number. I appreciate that. So because this molecule is symmetric, right? Molecule is symmetric. So no matter which side we count from, we'll get the same thing, right? Molecule is symmetric. So you say put a methyl group here. Let's put the methyl group here. See. Is this the answer? Right? Is this the answer?
Yes, sir.
No, this is not the answer, you know. Anybody can tell me why this is not the answer?
So you didn't put the H's on?
Yes, thank you, right. You need to put the H's on. So put the H's on in your mind mentally. H is gonna take some time for me. Okay, it's faster than me. All right. Let's move to the next question. Name another structure. Name another isomer of C5H12. C5H12 is called pentane, by the way. I shouldn't have told you that, but okay. C5H12. Somebody give me something. All right, wait. Two persons. I go take one from Davey, and I will take one from somebody else. So who's the next person who will go for me? Raise your hand. Let me see who wants to go next. Davey, I already select you in a Davey. Kimani, I go take from you too. Right, answer the last question. So I take Kimani, I go take Davey. So Davey, you go first. Come ready.
I am 2,2-dimethyl propane.
Okay, I go right way you tell me. 2,2-dimethyl propane. Wait, help me draw now, please. 2,2-dimethyl. Oh my lord. I never type this. Oh Jesus. Yeah, ready.
So 3 C's, 3 carbon to carbon single bonds. Then in the middle, draw a methyl group above it and a methyl group below it.
Okay, a methyl group above it and a methyl group below it. Okay. That's it?
And then add the H's.
Add the H's? All right. Kimani was the next person, right? Kimani, go ahead.
Sir, never mind, sir. I'm okay.
I mean, never mind, brother. Look how much other ice more is there. After Slick, you go back out. No. Kimani, come. Tell me a draw isomer. Because you and David can't draw the same isomer. Come. Kimani.
Sir, neopentane.
Show me how to draw that. Tell me how to draw it. You're drawing an isomer of pentane, brother. Isomer of pentane.
Sir, I'm thinking, sir.
All right. So while he thinks, let me got next question. You ready? You ready for me, Kimani?
So you can go ahead. You can come back to me.
No. We'll finish with the first and come. Come, Kimani. Come, talk to me. Quick.
Sir, I'm not sure. Isomers is not my strong suit.
All right, guys. If you struggle with building isomers, remember isomers is just a different structure of drawing it, right? So you draw this that way, you could have drawn it this way, right? You could have drawn a straight chain of 4. You could put on the group up here, right? Same thing. That's 5 carbons, they just put in the hydrogens. Right? You following me?
Yes, sir.
That's one.
So
That's
there'll be one methyl group.
this will be one methyl group on a butane. Yeah. And this is probably the same thing we draw above here. I think it's the same thing we draw up here. So these are isomers of the same of the pentane. Yeah. You could also draw a straight chain of 5. Look how much thing is there. This boy going to tell me. This young man going to tell me. Oh, can't find it. Look how much thing is there, Kimani. Look how much thing is there. No, just go draw the thing and play around. Say go find isomers. Yeah. All right. What's the functional group of ethanol? Answer quick.
Alcohol.
Alcohol.
Oh, wait, no, wait. Yeah, oh, wait. Yeah.
Who said no? Wait. Somebody else is there. Something else is there.
Wait, isn't
David
functional group what comes at the end?
I see the problem there. Yeah. So the OH, you could you could answer alcohol and put OH in the bracket.
Okay.
Mm-hmm.
So
all right.
Would it be COOH for the functional group?
No, the functional group is OH.
Okay.
COOH is, somebody tell me what COOH is, please.
Carbonic acid.
No,
Carboxylic.
Yes, carboxylic acid. Carboxylic. I know there's 2 names for that acid thing, but I don't think it's carbonic. You're thinking about a wrong thing. Yeah, you're washing some clothes there.
No, sir, I couldn't remember how to pronounce it.
Oh, you know, I can have carbonic soap. I was wondering if you're watching. You're washing. All right. Let's look at this reaction of ethanol, right? So table 2 summarizes the conditions and products of 2 reactions of ethanol. Complete the table by inserting reaction conditions and drawing the fully displayed structures of the product that would be formed. Take note that the type of product to be formed is given in the table. Right? So what do you react with alcohol with ethanol to form an alkene? Guys,
hydrogen.
You react ethanol with hydrogen form an alkene?
I'm not totally sure.
You could dehydrate it.
You could rehydrate it?
Dehydrate it, sir.
Dehydrate it? Okay, so how do you dehydrate alcohol now?
Concentrated H2SO4.
Concentrated sulfuric acid. Yep. You're going to need some heat with that, sir?
170 Celsius.
170 degrees. Yep, those are the conditions. So conc SO4. So remember to write it. Concentration. You just write CONC. That was Davey, right?
Sir Jabari.
Jabari. Long time I don't hear from you, sir. All right, tell me how to draw this alkene, please.
Ethene. Ethene, sir. C2H4.
What alkene are we drawing?
Ethene. Ethene, sir.
Ethene, or you can say ethylene. Yeah, ethene. You said ethene. Oh yeah, you've seen the right thing all the time. I was registered with me now. Yeah, so this is what you're going to draw here. All right, good answer. All right, guys. When you react, anybody follow with that? You just have to know. You just have to read the book and know it. When you react alcohol with an acid here, what do you produce?
Esther, sir.
Esther. All
Oh,
right.
yeah.
What conditions we need for this? Huh?
Yeah, I think it's the same thing, concentrated H2SO4 and heat.
Okay, that's true. So we're going to need the same concentrated. Why am I doing this? Okay. We need the same concentrated SO4. But what's the product we're going to farm?
Ethyl, ethanoate, and water.
Ethyl, ester. What's the ester? How we draw the ester? What the ester look?
So that would be the
Tell me how to draw it.
alcohol and the acid, but anyway, you would like remove the water, the H2O, so it would be like C, 2C, with the O, the double O at the top, the O that we wanted to the last C, then O again in front of it, then two more C's, and you would put H on the rest of all the C's, except for the double one.
Everybody following what's going on here?
Yes, sir.
All right, good. Remember, guys, you need to check up. You need to go check back on your ester formation, right? Check up on your ester formation. Not going through it now, unless a question comes up. Check up on your ester formation, right? All right, let's keep moving. Keep moving. All right. I don't think they go really fuss it too much on this, but what's the mass of electron? Anybody know the mass of electron? Relative mass?
1/1834.
Is it 1834 or 1836? 1830?
1830.
1836.
1836? You sure?
Isn't it 1840?
Oh my lord, all these numbers. Guys, I'm not writing anything right there, so check in the book. So fill in based on your information. What other particles are there in the atom?
Neutron.
Of a neutron, what else? What else is there?
Proton.
Proton, neutron. What's the charge? Charge on these.
+1.
Positive.
Plus. So positive on both of them?
No, neutron is 0.
So neutron is 0. Okay. What's the mass on proton?
1.
1. All right, good. Thank you. Very quick. See? Easy, easy. Keep going. All right, consider the notation of an atom, this. Or for we can draw this, right, guys? What atom is this? Anybody can tell me what atom this is? What's the name of this atom? Guys. Hello.
Is it phosphorus?
Silicon.
Phosphorus. Phosphorus is what group, sir?
Silicon, sir.
Silicon, right? It's right after, it's right under carbon because it's in group 4. Right, so this is silicon. We can draw the atomic configuration of silicon.
Yes.
Yes, so kind of shaky, you know. Oh my lord.
Yes.
All right. All right, let's see. Let's keep moving. Can we calculate the number of atoms in this? You know the formula, guys? You guys know the formula?
Sir, what up, moles?
No, it's not moles. They're trying to find the number of atoms.
Sir, I'm not sure.
Not sure.
Wait,
In case it come.
Sir. Well, sir, I don't really use formulas, so like I just use what I have. So 6.0 times 10 to the 23 is equal to 40 grams. Then X is equal to 80 grams. Then cross multiply
Oh, and say it.
1 18 times 6.0 exponential 4 point, wait, hold on, divided by 40. 1.2 times 10 to the 24 atoms.
24. Oh, sir, you sure that's the right answer?
Wait, hold on, let me recalculate.
Anybody know what's going on here? Anybody follow what's going on here?
Yes,
Anybody
sir, I follow.
Yes, sir.
Okay. So somebody else can the answer while he's calculating.
Did he say 1.2?
He said something times to the 24. Something times something raised to the 24.
Yes, sir. 1.2 times 10 to the 24.
Oh, 24. You know, I was thinking negative 24. All right, no problem. I was wondering how you get a smaller number. All right, no problem. That's right. All right, not a problem. Cucumber slices release water and salts added to them. Feast well when soaked in water. We know what's going on here. Quick and fast. What's the name of the process?
Osmosis.
Osmosis. Okay. The next example. I mean, if you know what osmosis is, I'm supposing I can explain what it is. All right, what is next example of osmosis?
Putting a leaf in sugar water.
Yeah. Insert your popular osmosis experiment here. I never did that one before.
Potato strips in water, in salt water.
I know about that one.
Plating salt on a slug or a frog.
You can talk about that as well. I mean, that's kind of dark, but okay. Who said that?
Travis.
Travis, oh my lord. Yes. Anyways, yeah, that worked as well, Travis. Travis here killing slugs. All right. Oh, I love these. Not really. Like at university, they get worse. All right, what reaction is going on here at number one? Number one, we see at compound A. What is compound A? Wait. Before I do that, the reaction. What the question is asking us to do, the question is asking us to look at the reaction scheme and determine the reactions, what reaction they undergo to go to different things, right? So probably they would want us to know, identify the type of reaction. Yeah, identify the type. Okay. So the person who's talking is breaking up. I hope that's not me. All right, so a compound, well, let's identify them first. So compound A is an alkene, right? Agreed?
Yes, sir.
Compound A is an alkene. Compound B is what kind of compound?
Alkene.
All right, so how do you move from an alkene to an alkane?
Addition reaction.
Yeah, we can do an addition reaction, all right. Or we can do something we call a hydrogenation reaction, right? Adding hydrogen. Same additional reaction. You guys follow me out with the term hydrogenation?
Yes, sir. That's when you add hydrogen to the alkene.
Yeah, but are you familiar with the term hydrogenation though?
Yes, sir.
Okay. I don't want to give you a term that they don't really put on the syllabus like that, or you're not taught. All right, compound C is what kind of compound?
An alkane.
What kind of alkane?
Kind of alkene.
Alkane.
A what?
Haloalkane.
Yes, a haloalkane. So what kind of reaction do we undergo to form a haloalkane?
Halogenation.
Halogenation. But the specific type of halogen here is bromine, right? I'll tell you something. There's only two types of things they can conduct halogenation with. They can conduct halogenation with bromine, or you can use chlorine. The other ones are either too small or too big. You can try, but the conditions, you can use chlorine, bromine. You cannot use fluorine. Iodine is too big. Astatine is too big. Yep. Yep. That's it. And fluorine is too electronegative. So it can probably start, but it probably just gonna break apart. There's just chlorine, bromine. And because of that, we can call this bromination. I don't know if you guys are familiar with bromination. Just adding that information there for you guys. So to know. So it's an additional reaction, specifically bromination. All right, which one is what do we have here at reaction 3? What's going on? We're forming combustion. Yep, combustion. Loud and proud. No second this is combustion. All right, and number 4.
Polymerization.
Polymerization. All right, good. Find suitable reagents. Okay. All right, suitable reagents. So from here to here, from A to B, what would you use?
Nickel, I think.
Nickel and you guys forget the most important thing here. You can't just use nickel. Nickel and what?
Heat. Water.
What about the hydrogen, guys? You're not going to.
Hydrogen, yes.
5 atmospheres.
Okay. Yeah, you have the atmosphere. You have the heat. You can use it. You can either use nickel. You can use palladium. You can use platinum. Yeah, those 3 things. Yeah. What about from A to C? From A to C, what do we need?
Bromide.
UV light, I think.
Bromide. What bromide is an ion or what's a bromide? You gonna need bromine water. You guys know bromine water? Get compressed bromine water. Guys, not here. Okay. Guess I'm talking to myself. You need bromine water and you need UV light. I think somebody said UV light, but they were whispering because they were kind of scared. Bromine and UV light. All right, guys. All right. Next one. Let's see what's going on. Given that R is an ethyl group, what's the molecular formula for this one? Given that this is an ethyl group, we know what an ethyl group is. Ethyl group is a C with the 3 carbons. So given that it's an ethyl group, what's the molecular formula? Someone answer quickly, please.
Give me a second, sir.
Let me get it before you guys, please. 1, 2, 3.
C3H6.
6? Okay. That's right. Let's clear my drawing. Thank you for that. Write chemical equation for reaction 3. Reaction 3 chemical equation. We know it just comes down to balancing, guys. So you know you go add oxygen to this and you go get back this, right? You balance it and you put on your state symbol. So how would we test A from B? Name a test you can test A from B. Give me a test.
Bromine and potassium permanganate.
You can use bromine and potassium permanganate. Yeah, 2 tests, good. There are tests out there. I don't think you come across those here. Bromine, potassium. Yeah, okay. Nobody's saying anything else. So bromine, potassium. Yeah. Describe it though. How when you use bromine, what would happen?
Sir, you will notice a color change. The alkene, the color will change from brownish to colorless. And if you're using potassium permanganate, it will change from purple to light pink or colorless. And no color change when reacted with alkane.
Okay, good. Thank you for that. Right?
Yes, sir.
Right. My lord. One of the students suggested reaction with these. All right. Some students investigated action of HCl with sample of sodium hydrogen carbonate. One student suggested the reaction will yield a gaseous product. Describe a test to identify the gaseous product to be formed. What test can you use?
Calcium hydroxide. So you can
Describe a test that you gonna use. Don't tell me the test you're gonna use. Describe the test. What you gonna do?
So we're going to bubble the gas through lime water, and if it turns cloudy or milky white, it is carbon dioxide.
Okay. Any other tests you have in mind, guys? The green splint going to extinguish, right? All right. State the physical properties of the gas. Okay. A sample of gas. Okay, a sample of gas in laboratory is collected in laboratory by downward delivery. State the physical property of the gas that support this method of collection. That's just downward delivery. Guys? Guys? The question is number 3 on the page, on the paper. Number 2, sorry. A sample of gas is collected in lab by downward delivery. State the physical property of the gas that support this method of collection.
It's going to be denser than air, therefore it's going to sink.
It's denser than the air? Yeah. So it's going to be denser than air, so it's collected below. All right, so chemical equation. We know to do this, right? What forms at the end when we add these together? What forms at the end?
Salt, carbon dioxide.
Sodium chloride, water, and carbon dioxide.
Good. I wanted the name of the salt, so I appreciate that. All right, some metals react with dilute acid to produce salt and aqueous products. Write an equation for reaction of magnesium with HCl. We can do this, right? What's the name of the salt? What's going to be formed here?
Magnesium chloride.
What's the formula of magnesium chloride?
MgCl2.
All right, yeah, that's good. All right, nitrogen is used. Some non-metals are used in agricultural industry. Nitrogen is used to manufacture fertilizers such as ammonium sulfate. Some farmers use ammonium sulfate fertilizers in the presence of a base. Explain why this is not a good practice. Anybody? Anybody? Hello? You guys just fall silent on me? All right. You guys know how nitrogen, ammonium, sorry. You guys know ammonium sulfate is formed? Anybody?
Oh, sir.
All right. Ammonium sulfate can be formed by acid-base reaction, right? So you can have H2SO4, and this can be reacted with let's see, ammonium chloride. Let's see, ammonium, maybe it's chloride. Let's use ammonium hydroxide. Let's run ammonium hydroxide. Yeah, this, what do you get at the end? Talk to me, guys.
Ammonium sulfate and
NH.
Ammonium sulfate and water, right? So tell me something. What kind of acid is sulfuric acid?
Strong acid.
What kind of acid is ammonium hydroxide? What kind of acid is ammonium hydroxide, guys?
Ammonium hydroxide is a base.
No, sorry, what kind of base is it? It's a strong base, weak base?
Strong base.
It's a weak base. Ammonium bases are weak, right? So if I have what happens now is that if I have a strong acid and a weak base, what's going to happen is that the product, the salt that is formed at the end is what we're going to call, it's going to be slightly acidic. Can you appreciate that?
Oh, so when you use it with a base, it wouldn't work because it would neutralize it?
Yep. But can you appreciate that this would be an acidic salt because it's formed from a acidic, not an acidic salt. Acidic salt is a different thing. It'd be acidic in nature because it's formed from a strong acid and a weak base. They can think about like the strong acid kind of overpowering the weak base at the end.
Yes, sir.
Yes, sir.
All right, good. So that's that. Phosphorus and silicon are two other useful nonmetals. These two uses of silicon and one use of phosphorus. Anybody hit me?
Silicon is used to make glass and electronic parts.
Phosphorus?
I'm not sure.
To manufacture phosphoric acid and to make pesticides.
It makes pesticides, yeah. But anybody here use matches? Nobody use matches? You guys, rich people use lighter? Anybody here use lighter?
Yes, sir.
Oh, okay. I was about to say, everybody use electricity and light them stove. All right. I really want to just find out who use lighter and whatever. But you see matches now, they use phosphorus to make matches as well. Phosphorus, depending on the allotrope of phosphorus, you have three major allotropes of phosphorus. You have red phosphorus, you have white phosphorus, you have black phosphorus, right? Depending on the allotrope, it can be explosive or it can be explosive or easily ignited. So they use phosphorus to make matches, right? That's next thing you can consider. Silicon is also used to make plastic, guys. Silicon can be used to make plastics. Silicons can be used to make toys. Silicon can be used to make lubricants. Silicon can be used to make a whole lot of things. Put your mind to it. You can find something there instead of a whole lot of things. All right, let's do the next question. Sulfur is a nonmetal that burns in air to produce a gas product that dissolves in water, gives a colorless solution. Identify the gas form and state the effects it will have on blue litmus paper. What gas will be formed?
Sulfur dioxide.
Okay, sulfur dioxide. When you dissolve sulfur dioxide in water, what do you get? Anybody?
Sulfur hydroxide.
Just add the things together, guys. Just add it together. Literally, just add it together. Just literally add them. What do you think you get?
Oh, sulfuric acid.
It's not sulfuric acid. It's probably sulfurous acid. Yeah. I get this thing here. And we know it's an acid, so it will turn this to what color?
Red.
Red, good. All right, so this is the end of this paper, right, guys? Let's see if we can get to 2019. Let's see what happens. Oh, 2020, but that was still a 2021 paper. Okay, January 1 is a PDF. Is that not okay? Okay, let's see. I think I don't want this already. Let me see if I can share again. Share screen. 2020. All right, here we go. It's familiar. Within some gas thing. All right. So the rate of reaction of magnesium with a solution of dilute sulfuric acid can be investigated by measuring how long it takes for a specific volume of gas to be produced. Andrew conducted 2 experiments to investigate factors that affect the rate of reaction between magnesium and sulfuric acid. In experiment 1, magnesium strips were added to 50 cm cube of 2 mole per dm cube sulfuric acid in a 250 cm cube conical flask. The volume of gas produced over a period of 6 minutes was measured, and some of the measurements are shown in figure 1. The data recorded for experiment 1 are summarized in table 1 on page 6. So this is the data, right? And they summarize it for you. They might have to in some stuff. Yeah, figured. You guys can read stuff, right? Yeah, just assume you guys can read the stuff then. Yeah, I guess we have to read them. I think I have to read them. Right. I think we have to read them, guys. Determine interval rate. Yeah, let's read it. Let's read it. All right, guys, let's start. What's the rate of reactions?
Changing concentration of a reactant with time.
Okay, like that. Anybody else? Nobody else?
Rate of reaction is the measure of time taken for a reaction to take place.
Okay, that's also good. Either of those definitions should be fine, right? Either of those definitions should be fine. Let's see if I can complete this table. Let's count. This is how much? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 6. The first one is 6 here. This first one is 6. I can draw this quick. 6. The second one. What is the second one? 11. Second one is 11. Right, 11. Third one is how much? Estimate this for me, guys. It's like a 0.5. 5, 6, 6.5. So 16.5. You guys can count these things, right? I'm just double checking. I would be ashamed for me to go through all of this work. You guys go in an exam and then there's somebody who is here going exam and mess up on the counting. Gonna never take time. Be ashamed. Be ashamed. This next one is 19. Okay, the last one after this one. All right, the last one is 20. Okay. Okay, let's see what's going on here in Excel file. You have 0, 0.5, 1, 2, 3, 4, 5, 6, 3. Oh, I'm not sharing my screen. Let me share my screen. All right. Oh, please stop writing. You guys see my Excel file, right?
Yes, sir.
3, 4, 5, 6. All right, so let's see. Oh crap, there goes my right. Okay, it's not fun. I have 0. My writing disappears, so I have to go back and get them over again. I know this is 20, I know this is 20, I know the one before it was 20. I know we had some weird numbers before. This one is 6, I think. 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 6. 5, 6. Okay, this one is 11. It's 16.5, I think that was 16.5. 0, 1, 2, 3, 4. I can't count. 0.5. Okay. There's a 19. 0.5. 1, 2, 3, 4, 5, 6. All right. After this, I have a 3. Let's just move this down. Cut, paste. 19. All right, I plot these against each other. Okay, let's go. So this is the plot again. It says from your graph, determine the time taken for the reaction to be complete. All right, look at the graph. What time do you think it would take for the reaction to be complete? The time is on the x-axis, on the y-axis. Time is on the x-axis. Thing is on the y-axis. Who is writing? Someone's writing on my screen. Go ahead. Talk to me. How long will it take for it to be finished? Reaction to be completed.
4 minutes.
4 minutes. All right. Why you say that, by the way? Why do you say that? Who said that, by the way? I can't even see the person who said that. First talking to me.
Sir, that does come to my mind. So we
Hall.
must say.
Why that come to your mind, Hall? It might be 4 minutes, you know, but why that come to your mind? Anybody agree with Hall? Something is in the chat. So after 4 minutes, the straight line indicates no more reaction. Yep, that's it. So 4 minutes is the answer because there's no more, if you look at the graph, there's no more volume of gas being produced. The volume of gas being produced doesn't change. So there's no more reaction. Yeah. All right, during which time period is the reaction fastest? Which time period? The first part, the second part, which period? You can say 0 to 0, 0 to 0.5, 0.5 to 1, 1 to 2, 2 to 3. Where is it fastest?
1 to 3.
1 to 3. All right. So that's the first part of the reaction, right? The first part of the reaction is the fastest part of the reaction. I haven't worked out 1 to 3, but I would say that 0 to like probably 1 is probably faster than 1 to 3. It's much better than over here. So the amount of gas being produced is much more than over time. But I would say 0 to 1.5. 0 to 0.5 or 0. Let me share back the question. Okay, you guys can hear me?
Yes, sir.
Okay, my thing just said my internet was unstable, so I have to double check real quick. All right. From your graph, determine the volume of gas produced at 2.5 minutes. Of course, you just it interpolates at 2.5 to find what goes on there in terms of volume. All right, let's work this out though. Let me interpolate and tell you what happens at 2.5. 2.5 interpolated, let's estimate that to be around 17, right? If 2.5 at 2.5, 17 cm cubed of gas is produced. Let's work out this question. You want to help me work out this question? All right, Neil, because it's easier than writing DM. It's right easier than writing CM cube. Someone want to help me with this question? You guys know what the word is out?
Yes, sir.
Talk me through it. Really hard.
Sir, I want that milliliter.
Yeah, it's the same thing. I didn't want to write CM cube. 1 milliliter is equal to CM cube. Let me undo it though. I could have written it. Let me write the CM cube. It's just more writing. CM cube. Yeah, ready? Wait, one person. Who talking? Not tall. The next guy who talking. Who's that? Kimani? Travis, what are you saying?
So you use, what do you use it for? Moles equal volume over molar volume.
Moles equal volume over molar volume. Okay. Talk to me.
So the volume would be 17 cm cube and the molar volume would be 22.4.
That's it? Can you just plug and play?
Divide.
So you're saying you divide 17 by 24, 22.4?
No.
Yes.
You don't think you should convert this? The 17?
Yes, sir. Yes, sir. Yes, sir. Should be converted.
When you convert it, what you get? When you convert it, what do you get?
0.017.
0.017. Okay. All right. Everybody's comfortable with this? Anybody don't use the formula and them wondering what's going on here? Anybody wondering what's going on? Okay. We're all good on this. Good. That's good. All right. Let's keep going. Andrew wanted to identify the gas produced. He placed a lit splint in a sample of the gas, which extinguished a squeaky pop. Deduce the identity of the gas. Hydrogen. Good. All right. Let's see. Next question. Andrew's second experiment required the use of same mass of magnesium, but in powdered form instead of strips. State the fact that Andrew is now investigating.
Sorry, is it something that has to do with surface area?
Surface area. Okay, next question. When magnesium and sulfuric acid is reacted, what do you get?
Magnesium sulfate and hydrogen gas.
Magnesium sulfate, hydrogen gas. All right, that's true. Are you still seeing my screen?
Yes, sir.
What are you seeing on my screen?
The questions, write a balanced chemical equation.
Okay. Let me wait up real quick. Putting on something we'll need for the later on in this course. Okay. Okay, let me go back to you. Here. Okay. List one factor other than the factor investigated by Andrew that can affect rate of reaction.
Sir,
concentration of this acid.
Concentration. Okay.
Yes, sir.
Okay. Done. All right, let's see what else is here. Define reduction in terms of oxidation state. All right, when oxidation reduction occurs together during a chemical reaction, the reaction is described as being redox. Some substances can act as oxidizing agents while others act as reducing agents. The equation for the redox reaction between copper sulfate, copper chloride, and aqueous iodine is given below. Define reduction in terms of oxidation states.
So it's a decrease in oxidation state.
Decrease in oxidation state. Okay. Decrease in oxidation state or decrease in oxidation number. Okay, good. Did you use the oxidation state of copper in this thing, the copper iodide? What's the iodization state of copper there?
The copper is 2+.
Copper is 2+, you sure?
Wait, would the oxidation state be 0? Because it's in a compound.
No.
Also, it's 4.
It's 4.
So would it be +1?
All right. Let me hear how you get 4 first and how you get +1.
Oh, because, well, copper has a charge of 2+. So and since there's a 2 in front of the compound, I would say it's +4, the oxidation state.
All right. I hear you. Why is it? Why you say it's 1? The person who said it was 1. Why did you say it's 1?
So I think iodide, the oxidation state for iodide is -1. So that means copper must be +1 to give you 0.
Yes, that's the answer. Yeah, because one is +1 and one is -1. One is -1, so the next one has to be +1 to bring it up to 0. Yeah. Okay. Let's see what else is there. With reference to the equation above, which substance is acting as an oxidizing agent?
Sir,
Which?
guess what?
Oh yes, I didn't realize you weren't seeing. Yeah, there we go.
Sir, copper.
Copper. Okay. Why would you say copper is an oxidizing agent? Tell me again, why is copper an oxidizing agent?
Sir, oxidizing agents are reduced, and in this equation, it moves from 2+ to 1.
Okay, thanks for that answer. All right, let's see if we can move on to the next question. Yeah, solution A is added in small portions to a small portion of aqueous potassium iodide, right? The colorless potassium iodine turns brown. State whether solution A contained a oxidizing agent or a reducing agent.
Oxidizing agent.
Why? Wait, both said oxidizing agent? Why?
Because potassium iodine is a reducing agent. And since there's a color change, oxidizing agent must be present.
All right, so that's one way to look at it. Another way to look at it is what is the oxidation state of iodine in potassium iodide? What's the oxidation state of potassium iodide, of iodide in potassium iodide? Anybody?
I minus.
It's -1, right? It's -1, right? So if potassium iodide is -1, and it moves from, we all agree that what is going on here is that iodine is being oxidized out. Iodine is being made into a solid. You see that that's what's happening? Solid. Iodine is being formed into a solid. That's what's going on here. If you have a solid iodine here, right? What's the oxidation state of this iodine here?
0.
0.
Beside one is 0.
Huh?
The solid one would be 0.
Okay, yeah. So we can see that it's increasing from -1 to 0, right? So in that case, it's also being oxidized. So there is an oxidizing agent here. Yeah. That's the next way you can explain it as well. I'd rather this way explain it because it's to the point. Because did you know that oxidizing agents can be oxidized? Did you know that? If you have an oxidizing agent, but you have a stronger oxidizing agent, the stronger oxidizing agent is going to oxidize a weak oxidizing agent.
Okay,
right?
sir. Yes, sir.
Yeah. So that's that. Chemical equation. I showed it something that looks at the chemical equation, but can we write the chemical equation? Can you just talk me through it very quickly? Talk me through the chemical equation. Nobody? Hello? Okay, so I'm going to take that as no, right? So chemical equation. We're adding A to potassium iodide. That's right. Potassium iodine is Ki, right, guys? Oh, my lord, my computer is lagging. What's going on here? It's not good. Hello? They add the solid A to the Ki. What they're saying is that this changes to I solid, and what's going to happen is that it's going to be the iodine is going to be displaced by the A. So the I turns a solid, and you actually get Ka being formed. You guys follow?
Yes, sir.
All right, so that's the answer right there. Hope that was too fast. Let me just keep it there for a little bit. Clearing it off in a few. Okay, when a piece of zinc is added to aqueous copper sulfate in a test tube, a reaction occurs as shown in the equation below. I'm clearing off this thing now. Move to the next question. Okay, this is the reaction. So describe what is observed in regards to the chemical reaction in the test tube. What will you observe? What will you see or hear or smell?
Sir, a color change from blue to colorless.
Yes, that's correct. Color change from blue to colorless. All right. One of the substances in B is acting as a reducing agent. In B, acting as a reducing agent. Describe a lab test that would be used to identify a reducing agent. Anybody?
So you can use oxidizing agent to identify a reducing agent.
You can do that. So give me an example of oxidizing agent you can use.
Acidify potassium dichromate.
You can use acidified potassium dichromate, and that, what color is that? You know what color that is?
I think it's orange to green.
It's orange, right? So when you add that to something that has a reducing agent, what's going to happen to that?
It changes from orange to green.
Turns green.
Okay. Going to change to green. Okay, no problem. Well, so it changed from chromium 6 to probably like chromium 4 or so. All right. What is already characteristics of homologous groups? C3H8, we did that in 2021 paper. All right, then we also stated, what homologous group was this again? C3H8.
Alkane.
Wait, alkane.
Repeat, sir?
Alkane. C3H8. What homologous group was that?
Alkane.
Alkane. Good. All right, write the molecular formula for the compound that has five carbon atoms of the homologous group. What's the formula of the compound that has 5 carbon atoms? Formula of the compound. So of course you have C5. C5H, what is going to be there? Tell me. I'll go right there.
H12.
C5H12. All right. You get that from the formula, which is CnH2n plus 2. Okay. Draw the structural formula of B, which has the formula C3H6. What kind of compound is this? What homologous series it belongs to?
Alkene.
Alkene. Good. So it has a double one. Well done. All right. So we'll answer that question here just now. And of course, we know that the one with 5 carbons would be called a
Pentene. C5.
Pen. C5H10. Yes. Okay, that's good. All right. So general formula for carboxylic acid. You guys know that? No? Any takers?
CnH2n plus 1 COOH.
You started out good, but you kind of repeat that.
CN.
H. I'm calculating in my head, that's why.
CnH2n plus 1 COOH.
That works for 1, that works for 2. Yeah, that's answer. This is answer, guys. What about one for alcohol?
CnH2n plus 1 OH.
Yeah. All right, the first member of the carboxylic group.
Methanoic acid.
Methanoic acid. Anybody know the common name for methanoic acid? It's something that when the ants bite you, that's the thing that stings you. It's called
formic acid.
Formic acid. Yeah, formic acid. All right. Alcohol. First one. Methanol. Okay. Methanol. Yep, that's it. Clear all drawings. Let's keep going. Jack was required to conduct investigation on electrolysis of concentrated sodium chloride solution. Yeah. Identify two ions present in electrolyte and include their state symbols. Okay, quick. Two ions in electrolytes with their state symbol.
Na plus and Cl minus.
What are the state symbols on those?
Chlorine is a gas.
And sodium and Na supposed to be solid.
No. Answer is both of them are aqueous. Well, they're ions, you know. They're ions. So sodium chloride dissociates. Sodium chloride is a solid which dissociates in water or dissolves in water to form sodium, aqueous sodium plus, and aqueous Cl minus. Yeah. Okay. State two factors that affect the discharge of an ion during electrolysis.
Sir, the concentration of the electrolyte and the type of electrode used.
Okay, that's two things. Anybody else have anything to add?
Reactivity series.
Reactivity series, that's definitely one of the tall ones. Okay. I think that should be everything, the major ones. All right. Predict which ions present in electrode will be attracted to the anode.
Cl minus.
Cl minus and what?
OH
minus.
OH minus. Okay. What happened to the Cl minus?
Turn it into chlorine gas.
Yes, it will turn into chlorine gas. So it would gain the electrons. So it would lose electrons and it would turn to chlorine gas. All right. Of course, you know at the cathode now we're going to gain those electrons and you're going to turn from sodium to sodium solid. Or depending on it, you can also have the formation of hydrogen gas, depending. Classification of substances. Conductors are non-conductors, right? Is metal magnesium ribbon conductor or non-conductor?
Conductor.
Plastic ruler.
Non-conductor.
Aqueous solution of magnesium chloride.
Conductor.
The conductor of okay. Conductor, they didn't specify. So the conduct electricity, that's right. So heat is not. I was thinking in terms of heat, but anyways, carbon is a type of non-metal. Name two uses of carbon. Two uses of carbon, any carbon.
And sir, to cut like things.
So how is carbon used to cut things? What form is it taking in? Carbon is used to make diamonds, which is then used to cut things. Yeah. Carbon is also used. How is carbon used? Carbon dating, guys.
Sir, yes, sir. And carbon 14 can be used to tell the age of an organism that was once.
Was once alive, you said?
Yes, sir.
Okay. Yeah,
And
so carbon,
well, that is used in carbon dating.
I mean, carbon dating is about putting on an age to it, you know. So the same thing you're talking about, the determining when how old something was when it died, that's carbon dating. That's carbon dating. Yeah. So you're dating how much percentage of carbon is left in it, right? All right. Compound C is a sweet solid compound. Let me see if I can name this for you. Do I know this compound? Okay, I think I know it. Name the homologous series it belongs to. I name the compound.
So it belongs to the ester. And it's methyl propanoate.
Methyl propanoate. All right, that's correct. Anybody? Oh, yeah, I just thought it was correct. The methyl propanoate is they used in they say used in cologne. Yeah, I was about to say the same thing. Anybody into fragrances? Anybody here into fragrances?
Yes, sir.
What fragrance you into?
Sir, citrus.
Into citrus fragrances. All right. So this compound, just fun fact, right? Just to distract your mind is because the guy's probably weary. So this compound here, anybody know Bentley? Like any Bentley cologne, like Bentley for Men Intense, or let me see if I can know anymore. Anybody know that, or no, you can't use that either. I think that's the old one. Oh wait, you can use that. Anybody know Stronger With You? Stronger With You by Armani Code. No? Nobody into. You say you're into fragrances. Where's my fragrance person? All right, so basically this smell like rum. All right. It smells like rum. How rum smell? The sticky sweet rum. All right, let's keep moving. Draw fully displayed structural formula of the two molecules produced when this is hydrolyzed. What two things go before when this is hydrolyzed?
Methanol and propanoic acid.
Yes, that's correct. That's correct. All right. So ethanol is widely used as a solvent for cosmetics and perfumes. State the name of compound D and identify the reagents and conditions needed for ethanol to be converted into compound D. Hit me. All right, what kind of process is going on here to convert from ethanol to D? What's the name of the process? Guys.
Sure, I think it's when it reacts with potassium permanganate.
I think you're overthinking it. You're going to ask, what's the name of the process? Move from here to here. What's the name of the process?
Oxidation, sir.
Oxidation, right? So that being said, what do you need to do to oxidize this? You need a Oxidizing agent. Yeah, right? So if you can identify that, then you can say, okay, potassium permanganate. Potassium permanganate is an oxidizing agent. So yeah, you can use that. Right? You can also use who here, anybody here, you guys are young, you're not supposed to be drinking. Can't ask that question. Who here drink? I mean, we're in Jamaica, nobody not really don't. Not water, obvious to people. People don't try to be smart with me. Who drinks alcohol? Even silent as a mouse. Nobody not coming for you. Yeah. All right. For those people who drink alcohol, who here drive? Who here practices to drive or going for a driver's license? Travis, I know you drink. All right. So Miss Hall, right? God forbid you're on the road and you're drinking. You go to a party with your friend and you drink something, right? There's going to be ethanol. You know, ethanol is what you're drinking, right? So there's going to be ethanol on your breath. Understand? So there's this test that the police do called the breathalyzer test. You guys know the breathalyzer test? This all you know breathalyzer test?
Yes, sir.
Yeah. So the breathalyzer test now, they have this compound. Anybody know the name of the compound I'm using the breathalyzer test?
Potassium dichromate.
Yeah, potassium dichromate. So this orange thing. So what happened is that they pull you over and the police say, all right, can you walk in a straight line? Right, Miss Hall? Police say, walk in a straight line. And Miss Hall say, all right, let me walk in a straight line. And she's stumbling here and there and all this. All right, let me test her. And so Miss Hall, breathe into this for me. God forbid, right? Miss Hall, breathe into the thing and the thing turned from orange to red, right? What is going on there is that the ethanol in her breath, right, is being oxidized by the dichromate. Dichromate is a +6 ion in the form of potassium dichromate. It has an oxidation state of +6. And when Miss Hall take up her breath, what smell like? Miss Hall, drink any? You drink alcohol?
No,
Miss Hall, you know what, Miss Hall? Let's say Miss Hall is rich, right? Miss Hall go to rich people thing and Miss Hall drink Hennessy, right? I don't anything that's more expensive than Hennessy. I'm really a drinker, but yeah. So Miss Hall drink Hennessy and the alcohol in Hennessy touch the thing now. It's going to oxidize you're going to reduce the oxidation state of the chromium from +6 to something else. And at the same time, right? The chromium in the dichromate is going to give the ethanol another oxygen here and form this, right? The conditions needed for something like this to happen, you're going to need the reagent, right? And perhaps you're going to also need some heat. Yeah? But you understand what's going on here? Nobody understand what's going on here?
Yes, sir.
no, sir, but I do not know.
You don't know anything that's going on here? Okay. Don't know anything that's going on here. Please continue not to know anything that's going on here. Know it on exam though. All right. Explain how ethanol can be made from the fermentation of sugars. Let me double check real quick and see if that's actually on the list. I really want you guys to answer this question. Let me pull up the thing I sent you guys in the group. I don't think that's on the list, you know. Let me see. Extraction, it's not on the list, but let's answer it for good measure, right? So Marks, yeah, talk to me. That was all talking.
No, sir, right.
Oh, okay. Miss Wright, go ahead.
Yes, sir. When yeast ferments sugar, it produces ethanol and carbon dioxide.
You were right there for several marks, Miss Wright?
Repeat that, sir.
You're going to write that one sentence for several marks?
Sir, I don't know anything else.
All right.
Sir, would the equation be the one opposite of Photosynthesis?
It is similar to photosynthesis, in the sense that you start out with glucose, right? And that's the only similarity it has, because photosynthesis doesn't really produce any substantial amount of ethanol, right? So that's where similarity ends, right? So of course, if from glucose you produce ethanol and you produce carbon dioxide, right? It's a thermic reaction. And what happens is that that ethanol is what's required for the alcohol being made. I really suggest that you guys read the book. You guys have any reading book like for this? No response.
Yes.
So you can read the book and then determine what's going on there. I don't see it on the list, and for me to go through right now, I don't think I can go through that right now.
Okay,
All right.
isn't fermentation respiration?
Search in the chat.
Oh, with and glucose alkene, glucose not an alkene, but when a glucose is in the presence of enzyme, it produces, yeah, basically that's what's going on. That's what's going on basically. Yep. Pretty much. So whatever what Britannia said was that glucose in the presence of a zymase is an enzyme that's found in yeast. Yeah. Ethanol and carbon dioxide is produced. Yeah. All right, state one other use for ethanol. Guys, I just gave an example.
So it is used to make alcohol.
Yes. No, what kind of response is that? Oh Lord. It's not used to make how you use alcohol to make alcohol.
These are ethanol.
Ethanol, aren't seeing the question? Travis, give me another use for ethanol.
Clean woods.
Clean what? Okay, clean what? These people are so scientific. Wounds. You go put ethanol on your wound? Oh my Lord. I hope you don't get cut. It's crazy. You won't put ethanol on your wound? That is crazy. That's crazy, my friend. What about drinking? No, these people are not Jamaican. You guys are not in the Caribbean. It's straight, not a word. You're not going to put ethanol in your wound. Trust me. Let me see if I can come with an example other than drinking. Ethanol. Ethanol can be used as a solvent. Ethanol can be used as gasoline. Ethanol can be used as fuel. It's very easy to light. Ethanol. Yeah, it can be used like lamps. You have ethanol lamps out there. Ethanol can be used for so many things. This lady go put ethanol in her cut. Miss Hall, may God be with us. All right. Let's see. Figure 2 shows experiments with iron nails exposed in different conditions. All right, so you have iron in water and air, iron in bottled water with oil over it, and iron in dry air. There are 2 conditions necessary for the corrosion of a metal.
Moisture on air.
Moisture on air.
Yes, sir.
Okay. Moisture. Okay. I mean, you can use the water, but all right, moisture. All right. State what though? say which conditions will corrosion occur? Which one will corrosion occur? A, B, or C? Which one will corrosion occur? Will corrosion occur in number in A?
Yes, sir.
Okay. Will corrosion happen in B?
No, sir.
Okay. Will corrosion happen in C?
No, sir.
Why corrosion will not happen in B?
Sir, because oil is present. Oil is present, so it's blocking the air from reaching the nail.
Okay. And it's also boiled water, so free gaseous particles were more like have been like taken out of the water. All right. So just why boiled water was covered with oil. Okay, you just said it was blocking the air. Okay. All right. One alloy of aluminum and its use.
Manganalium.
No curse better than me.
Razor.
Don't curse bad word on me. Somebody want help? Somebody want help Travis? Or somebody want here help Travis? Travis. I don't want Travis cursing the bad word and keep them straight. Somebody want help Travis? One alloy of aluminum. Nobody else?
Sir, repeat what's the action?
My lord. You guys are sleeping. All right, if you're sleeping, all right. Let me take a 1 minute break. You guys stand up, stretch, go get some water. Wash in the face, and you wash in the face. I'm waiting. But I'm talking and nobody now listen to me. You guys are sleeping.
Sir,
All right, Sam. That's right.
Duralumin.
Duralumin is one aluminum, is one alloy. I'm waiting for others. I'm waiting until 4:17 for people to wash them face and drink some water and come back. I take a little break. I take a 1 minute break because everybody just falls silent. Travis go curse bad word, and everything just falling apart. So I was waiting a little bit. All right. I hope you guys. All right. It's the time come now. It's 4:17. You guys come back with stress. Oh, why stress? Talk to me. It's all.
Like, I just feel unmotivated. Like, I just can't study. I just don't know nothing in chemistry.
What do you mean you don't know nothing?
No, only thing I know, sir, redox and moles and them something, but I don't know nothing else.
Like what? What else you want to know?
Organic chemistry, sir.
You never answer. You didn't answer in it. So all the organic chemistry I've been doing, you don't know one thing I've been doing?
Sir, I don't know, no. All the thing I know are pentene and them something there.
So what you're saying, Paul, what you're saying is that you only know the part of organic chemistry I've been doing? That's what you've been saying? That's what you're saying?
Not everything.
All right, after every question I ask, everybody follow it? And Miss Holly don't say a word to me, Miss Hall.
Much time I said no.
Miss Hall, what do you not understand in organic chemistry, Miss Hall?
Sir, but you said no, I tell myself I'm supposed to go read.
All right, read up on what topic? Let me see what else. Let me see what topic I tell you to read up on.
Organic chemistry.
All of organic chemistry?
Sir, I remember what we did the first paper.
We're reading the first paper. All right. I mean, there's some part of organic chemistry you have to read, right? I can't teach you everything in organic chemistry. You know the homologous series, you know certain things, but for like reactions and things like that, you have to read for reactions. I can't teach your reactions. Not that kind of session. So I need for you to like when the exam start, Hall.
The 31st.
31st? All right. What I want you to do? All right. You finish all the syllabuses?
No.
What syllabus you don't finish?
For bio, physics, subject, geo, Sir, come like all of them. Applied maths. I don't know, all of them.
Applied maths. Okay. All right. Tell you what. You have a timetable?
Yes, sir.
How much? All right. This is a little bit off course. Let me see how much time I have left in this. Let me finish this, right? I'm going to finish this paper, right? And I'm going to open up the floor to talk to you guys for a little bit, probably like a 10 minutes, and talk you through your problems or whatever, right? Let me finish this, right? So there are two alloys of aluminum, right? I think, right, you're the person who told me the duralumin. You told me duralumin. Was it right, or was it? Yeah, I think it was right. Okay, yeah. And the bad word that Travis was trying to say was megnalinum. Oh my lord. Get me sometime. Megnalinum. Yeah. Is megnalinum? I think there's an A in there now. Probably magnalinum. Yeah, magnalinum. Yeah. So there's magnalinum and duralinum. And both of them are used basically in aircraft. You can think about that. Aircraft. Explain why the corrosion of aluminum is beneficial. Anybody? Quick and fast. Start with an A. You guys know about anodization? Yes, anodization. Anodization. Everybody know what anodization is? Who does not know what anodization is? If you don't know what it is, raise your hand. All right, Lynch, let me tell you what anodization is, right? Anodization is when you have aluminum and it reacts in the presence of oxygen, right? Atmospheric oxygen, and it forms this thing called aluminum oxide. Aluminum oxide is a white powdery thing. Like aluminum is shiny in and of itself, but aluminum oxide is dull, gray powdery solid, and it's not very reactive. So what happens is that anodization happens when that white powder or that white solid is formed on the surface of the fresh aluminum, and it kind of it protects the inner aluminum from being oxidized. So it just stays on the surface and doesn't allow further oxidization. Understand? Yeah? Yeah, no problem. It's different from rusting, right? Because when rusting happens, the rust doesn't stay on the iron. The rust falls off the iron. So when it falls off, new iron is always being exposed and it can be attacked and be oxidized. All right, write a balance equation to show product when aluminum is left exposed to air. So basically the same thing as with you. Aluminum exposed to air, you just write aluminum plus oxygen, give it aluminum oxide. Aluminum oxide is what's the formula of aluminum oxide? Anybody? Aluminum oxide.
Al2O3.
Al2O3. All right, that's good. All right, so this is 2020 paper. We just finished that. So far, I think we did like 4 papers since day, right? We did 2020 paper for January. I mean, we do 2020 paper for June, probably. No, don't do that yet. We'd like 2 paper or 3 paper. 2 paper. We did 2 paper. 3 paper. I think we did 3 paper since day. All right. So let me see how best I can facilitate your question. I was speaking to Hall. Hall says she have a timetable, right? Let me see if I can pause this recording real quick. No. Okay, yes. Thank you for the reminder, Jonah. All right, Michael and Jennifer were assigned a group project to investigate the effects of surface area on the rate of reaction between zinc and dilute sulfuric acid. They obtained 6 different grades of granulated zinc. The grades represent the average size of the radius in microns of the granules. 6 experiments were conducted using the different grades of zinc granules, which were reacted with an excess of 0.5 molarity dilute sulfuric acid at 25 degrees. The same mass, that is 0.55 grams of zinc granules, were used in all experiments, and the time taken to collect 100 cm cubed of hydrogen gas was noted in table 1. Figure 1 shows the stopwatch readings of the time taken to collect 100 cm cubed of hydrogen gas. Right, so this shows the time taken to collect the 100 cm cube. I think we have to read as well. We have to read up and fill out some table. Let's double check. Yep, figured. All right, talk me through this. So this first one is around 11. I'm going to do this. I'm going to write out these answers, but you guys will have to work out the rates for me. All right. So let me write out the answers. So this first one is 11. 6. Who's coming in? 1, 2, 3, 4, 5. The first one is 11. The second one is 20. The third one is 32. 20 and 32. Let me draw. 20. We have 32. You also have 43 and 52. 43 and 52. And 52. And then the last one is supposed to be around 54. 55 plus 4 is, call it 58. It doesn't get 59. 58. All right, calculate these rates for me, please. Talk to me.
Sir, the second one is 0.050.
0.05. Okay. Next one, guys.
0.031.
Thank you. Next one.
0.023.
23.
There is 0.019. 0.017.
0.017. Okay. Just checking if you're all here with me and everything. All right. So these are the things here. And what they're saying is that we're supposed to use these values and plot a graph. So the graph here we're going to plot. Right? You must realize that them love asking you to plot graph. I should probably have you guys plot this one now. Let me delete this real quick. Delete that real quick. So you plot the graph and rate of reaction. The graph is going to look like this. Let me do a quick sketch for you. The graph will look something like this. Right? Something like this the graph is going to look. Something like that. That being said about the graph, explain how the trend in rate of reaction relates to the surface area of the granules. So let's go back up here. Oh, add up the thing up here. Let me see if I can reverse. Yeah. So how does rate of reaction, how does the size of granules affect the rate of reaction?
Sir, the smaller the granules, the faster the rate of reaction.
Okay. All right, that's good. Let's answer. So the smaller it is, the faster. List 3 factors other than surface area that can affect the rate of a reaction.
Presence of catalyst.
Particle size.
Particle size, concentration is one. Particle size would be something similar to area, surface area. There's the next one.
Catalyst.
Catalyst.
The temperature.
Temperature. Yeah, temperature. Catalyst was said already. I think Hall said catalyst. Either Hall or right. Yeah. All right. State one safety precaution that they could use during the experiment. So during the experiment, they were mixing. Or were they mixing? Zinc. You're putting zinc in HCl probably. HCl they're putting it in. Yeah, they're putting zinc in sulfuric acid. One safety precaution they could have taken.
Yeah, personal protective gear, like gloves.
Personal, or glasses, yeah. So that's one, definitely. So just one way in which they could have controlled the temperature during the experiment. How can you control the temperature? Let's see what they did. I didn't hear what you said. User? I didn't hear what that person said. Somebody hear what the person said? Can you repeat it for me? Person kind of broke up. Or anybody have any other ideas?
So you could use a styrofoam cup.
You can use a styrofoam cup. Okay. Yeah, that's about it. You can use a styrofoam cup. You can use a water bath as well. Yeah. You just make sure that the water bath is at a temperature where it doesn't suck. It doesn't suck the heat from the reaction, right? You want something that maintains the heat of the reaction. So I don't think a water bath, maybe the water bath is not really the best thing, right? Because when you put it in the water bath, right, all you put it in the water bath, let me tell you what water bath go. The water bath is going to either, if the thing where you put in the water bath is not the same temperature as the water bath is either going to take heat from it, right? Heat is going to either flow from the thing to the water bath, or the water bath heat is going to flow from the water bath to it. You understand? Because if you do a reaction and the reaction is hotter than the water bath, the reaction is going to try heating up the water bath, if that makes sense. And if the water bath is hotter than the reaction, the water bath is going to heat up the reaction. If that makes sense, all? So can you control water bath or no water bath? I don't think water bath would be a suitable thing. Just use a styrofoam cup. You want something that would prevent heat loss and potential heat gain from environment. So probably an insulated container. Cup, colorimeter, styrofoam cup. That's about it. Water bath wouldn't be the best thing, but I can't determine how much heat it's going to go by. All right, let's keep going. When zinc reacts with this, we know it's going to form hydrogen gas. But what's the salt that's going to be formed?
Zinc sulfate.
Zinc sulfate. Yeah, zinc sulfate. What was that? Travis or Kimani? Look, I'm gonna get everybody wrong. All right, so we worked out something like this already. Travis, all right. Worked out this already, right? But let me see if I can talk it out again. Calculate the total volume of hydrogen gas produced from RTP. Produce a RTP from 50 grams of zinc granules, right? Total volume. So we need the moles of hydrogen gas. So Let's see. Where are we? Where are we?
So wouldn't that come from the equation?
It would mole ratio HCl, sorry, H2SO4 plus zinc. Give it that. Not necessarily. But how would you calculate it from the equation? How would you calculate from the equation?
So could we use the mole ratio between zinc and hydrogen?
So you get the mole ratio between zinc and hydrogen. Okay.
And 0.55 gram of zinc was used. So we could use that to determine the amount of hydrogen used.
That's true. All right. So how much zinc moles do we? What's the mole ratio between zinc and hydrogen? All right, this here. What's the mole ratio between zinc and hydrogen, guys? Guys? What are you talking to me?
Repeat, sir. Repeat.
Mole ratio between zinc and hydrogen.
Seems like a 1 to 2, 1 to 1.
1 to 1. Okay. Okay. So here it is. The 1 to 1. So it's a 1 to 1 ratio. So how much moles of zinc was there? I think Hall was talking us through, but I decided to go a little bit slower so we can all follow. So if we have 0.5 grams of zinc, how much moles of
Right, sir.
Right? Oh, right. It was telling me. Okay, no problem. If you have 0.5 grams of zinc, right? And how much moles is this? 0.5 grams. Yes. 0.55 divided by 64.2. The RMM is there on the screen. 0.0086. 0.0086. Right? So we have the same amount of zinc moles, we have same amount of hydrogen moles. So we get this now. What do we do from here, right?
So we use we put that over 24,000 cm cube.
24,000 cm cube.
Sir, RTP.
Okay. And then what happens from here? What happens from here? Do you hear me? Let me see if you hear me. I think my wife.
I'm trying to process it.
Okay. Somebody want to help her in the meantime?
Sir, would the amount we get be the volume?
Yeah. It will. It will be the volume. All right. So amount of moles over RMM over molar volume is equal to volume. Yeah. So look, it's a very small amount of volume. 0. It's small and it's a lot of zeros. So let me just write it in scientific form. It's 3.6 times 10 to the negative 5, I think. Probably negative 6. Let's count these zeros. 3.6 times 10 negative. 6. We'll count the zeros. 1, 2, 3, 4, 5, 6, 7. Okay. 7. All right. There we go. That's the answer. Of course, this is in cm cube, right? All right. Let's see what else is on this paper. Speak about periodic. Explain why the elements are placed in periodic 3. Why these elements placed in periodic 3? Very quickly.
Because all of them have 3 energy shells.
All of them have period 3. They have three. Oh, energy shells. I heard empty shells. I was like, what? Energy shells. Yes. That's right. All right. Which element in period in table 2 forms an oxide that readily dissolves in water and gives a solution greater than 7? This is a little bit of inorganic. Which of the following forms an oxide that is basically, it's saying which one forms a basic oxide. All right, so let's think about the oxides. Is sodium oxide basic? Guys? All right, so we have a gap here in knowledge. Huh? Sodium oxide basic, guys?
I don't think so.
You don't think so? All right, as you go across the group, guys, let me tell you this. As you go across the group, it's around the last part of the syllabus. But as you go across the group, the acidity increases. The acidity increases as you go across the group. Right? So that means that, think about it. Is sulfur dioxide acidic?
Yes, sir.
Yeah. Sulfur dioxide is acidic. You guys know bleach? Of course you know bleach. You know chlorate. Chlorate is in bleach. You know chlorate? Chlorate, ClO3. You know chlorate? I think it's ClO4 actually, chlorate. You know chlorate, guys?
No, sir.
All right. Yeah, this is what's in bleach. The mixture of this and ClO3 that's in bleach. And it's acidic, right? Sulfur is acidic. Think about pH. What about PO3 or PO4? Is PO4 acidic? Think about HPO4. Is HPO4 acidic?
Yes, sir.
Yeah. I mean, PO4 is acidic. This whole thing is acidic. PO4 is an acidic thing, right? So as they go across, acidity increases, yeah? So that's why you have sodium oxides being basic and stuff like that. Right? Sodium is actually the answer. Sodium oxide is basic. And magnesium oxide is also basic. Aluminum oxide is basic. But remember, you have to remember your solubility rules when it comes down to this to link it back together. Right? We define allotropes already. And let me clear this off my screen. We define allotropes already. Configuration of electrons in sulfur, of course, we can do that, right, guys?
Yes, sir.
All right, so we can, what kind of bonding occurs when sulfur reacts with chlorine? What kind of bonding is that? Sulfur chlorine is here. Sulfur covalent, good. What's the formula of a compound which form when sulfur reacts with chlorine? Just give a random formula. All right. So sulfur reacts with chlorine, right? So you can work it out yourself. You can work it out. So we know that it's covalent because both of them are what kind of atoms? They're non-metals, yeah. Yeah. This is good. All right. So we know that sulfur has how much lone pairs? 6 lone pairs or so. Let me see. Right? And chlorine has how much? Chlorine has 7 lone pairs, right? So we can see that chlorine would want how much more? Chlorine would want 1 more, right, to pull up, right? So chlorine can probably share 1 with this. So one of these can share with chlorine, maybe. One of these.
Another chlorine.
You go need the next chlorine on the next side here, probably here. Put it there, share, and then this would be a potential thing because these and this could share, right? And this could share, right? You see that, guys?
Yes, sir.
So the thing would be SCl2. This could be a potential formula of something. So this would be the answer for this one, SCl2. Right? Let's clear that. Dot class diagram. Oh wow, that's so convenient. It just happened to be right there. So that's crazy. All right, polymer. We know what a polymer is, right? We know what a polymer is, guys. A polymer.
Yes, sir.
What's a polymer?
So it is a long chain macromolecule consisting of repeating units called monomers.
Yes. That's that. And of course, we know there's difference between condensation polymerization and addition polymerization. If we don't, we can always refer back to our notes. But condensation happens. If you think about condensation, what comes to mind? Or if you think about addition, what comes to mind?
Adding something.
Alkene.
You think about adding, right? So you're adding on to something. If you think about condensation, what comes to mind?
You're making it smaller, you're taking away something from it.
And if you look at how addition polymerization happen versus condensation polymerization happen, you will see just that. Because in additional polymerization, right? Am I over time? I'm just on the brink of time. Let me see if I can finish this one and then I can close up, right? I don't want to keep you guys here too late or anything like that. So in additional polymerization, right? We see that things are literally being added onto each other. There's literally add-on. I'm trying to think of an example, so I can show you. But that's how I remember it. It's literally being added on to each other. I can think of probably like an ethene, right? Think of an ethene. Let me see if I can draw this quick. Think of an ethene. Ethene reacts with itself. You have an next ethene over here, right? It's literally just going to add on. These things just going to add on and make a whole long chain, right? It's just going to be like, okay, one ethene there, let me just make a long ethene. That's how I understand addition and polymerization, right? Where condensation and polymerization normally happen when you have like a diacid, right? You have a diacid. Let's say it's something like this. The O. You have a OH on this end. And what happens is that diacid is condensed, or diacid is condensation reaction. Right up through chemistry mean the removal of water, right? That's what condensation means in chemistry. So this actually reacts then with probably like an amide, like a polyamide, or a it can react with amino acids, right? And it can react and form a longer chain at the expense of a water molecule being expelled. So let me just, I think I drew on the wrong side of amino acid here. For example, I would have the N here, right? You guys know what amino acids are, right?
Yes, sir.
Yeah. So you have the N there, and it goes over to the C, double bond O, OH. There is no name of amino acid, but yeah, and basically what happens is that this part comes off, right? And you form a linkage between this, the C, and the N here. They just form the linkage here and continue the chain that way. You can continue this way as well. Sometimes it don't have to be a what you call this thing? Amino acid. It can be a diamide, for example. I can imagine this nitrogen on the next side as well, just continuing as well. So it can happen a whole lot of ways. But I sent a few books in the group, right? During our break time, I sent a few books in the group. Feel free to consult those books, right? If you don't feel like reading, then like there are other ways you can get information. It might be a little bit more expensive or whatever. It might be taxing. There are different ways to get information, right? But I'm presenting you the most economical way. Feel free to shoot any questions by me. If you have anything to ask, I'm always there in the group. Just as I said, keep it chemistry related, and I'll see what happens, right? So I think this is a very insightful session. We finished 1.5. We look at this paper, we're halfway through. Basically, we have 1 page, 2 page, 3 page, 4, 5, 6, 7, 8, 9, 10 page, 11, 12 page left. Oh, 22 pages are there, and we were at page number, we're not halfway yet. We reached almost halfway. 22 pages, I reached page 10. So not bad. All right, guys, that's a wrap. Nice meeting you. I met a few new persons here. Right. So I met with, let me see my chat. Met with Jade. I don't think Jade came back here. Met with Jade. I met with Lynch. Lynch didn't really speak much. Sent a few messages here and there. Mr. Davey, Jabari, Edwards, Hall look like drop off. Hall will be fine. You'll be fine, Hall. Air Force 9. You know, I know some people are here from out of town, right? Is the majority of us here from? Just ask for my own curiosity. Majority of us here from what school are you here from? I'm just gonna go down list and inquire what schools you guys are here from. Anthony, I think Anthony is in 4th form. He's from, what's in that school in out of town? Westwood? No, not Westwood. Anthony? All right, Lynch. What school are you from, Lynch?
Yes, the Manchester High School.
Oh, she put the V on the front of it. Okay, the Manchester High School from Lynch. Anthony, what school are you from again?
Homewood Technical.
Homewood, yes. You're running school. We have Homewood, we have Manchester, we have Christian.
Yes, sir. I'm from the Denby High School.
Everybody start put D and them name now. All right, no problem. Gabriel. Oh, sorry, Sir Davy. Davy.
I'm from the Arden.
Arden. Okay, we have Arden here. One person in town
I'm
so far.
from the Arden. Yes, sir.
Wait, Mr. David, the last time I checked Arden, do I was the on front of it now, but all right. Jabari.
From Cornwall College.
Clarendon.
Cornwall, sir. Cornwall College.
Cornwall. Oh, Cornwall. That's in
St. James.
I was trying to remember the place exactly. Moby, somewhere in Moby.
Yes, sir. Moby.
Remember that road. I remember that road. All right. Orange Street, yeah. Around there. So who else on this list? Edward.
Immaculate Conception.
Now we have two town people. Edward from Immaculate. All right. Thomas.
Sir Alpha.
Alpha. So Alpha do have D in front of it. All right. So Immaculate and Alpha do have D. Everybody else have D though. McLeod, where are you from?
Different grade high school.
Where? The Cartridge?
Different grade high school.
All right. I didn't get the name of that high school. Oh, Fern Gully, you said, right? I hope she said Fern Gully.
So she said.
Oh, Fern Cut. Oh, where's Fern Cut, ma'am? I don't know Fern Cut. Saint Anne. Okay. Right.
Sir, the Westwood High School.
Wait, I think Right is in the chat already, you know. Westwood. There's a bunch of out of town people here. All right. Chevanese.
Alpha Academy.
Alpha. So two Alpha here. Earl.
Westwood.
Westwood. Two Westwood as well. And Travis. Travis saying it's in the Travis, if I get the D, man, Travis, there's a D on you. There's a D. If I get the D. All right, guys. It was a wonderful session today. Just here getting ready to oh, I forgot. Hall, I didn't ask you what school you went to. Oh, she wasn't here when I asked. All right, Excelsior. That's around 3 different schools in town. We have Arden, we have Alpha, we have Excelsior, we have, where else we have? Immaculate 4. I can't count. We have Westwood, we have Ferncut, we have Ferncut. I can't pronounce that name. Westwood, we have the running school.
So it's Court.
Pardon? Look, I have to go to school for spelling. But all right, guys. It has been a pleasure. If anything, you can contact me in the group. I think there are other uses for this link at this moment. So I think we have to come off them time. All right, guys, been a pleasure. I'm looking forward to our discussion in our group. All right. The recording will be made available in due time. If you have any questions regarding recording or anything like that, I think Johanna is here. You can always shoot things by her, right? You can any questions you have, you can shoot it by her. I don't know if she can accept questions now, but on my behalf, on my end, we're finished for now. All right, guys. Have a wonderful day.
Same to you, sir.
All right, no problem.